that's good enough. Cool.
Test, test, test.
Which one should I use for the black one? Okay. For everything.
This is goes to the room. This is for the recording.
Oh, okay.
But yes, you can just speak normally and it'll catch it. But this one is the one that you care about.
Oh no. Oh yeah, so
Do you still need to test? Can you? Please. You don't have audio. No? Okay, okay.
I believe 3D printing technology not only should allow complex geometries, but also
Is it on? Okay. Sure. He didn't turn it on yet. Yeah, for the recording. So yeah. Yeah. Yeah, room mic. I don't think it's on. This is not echoing. This is for recording. I don't hear any echo too. I don't see any switch over here. Is it on or? Oh, yay. All right. Can we start? We are already out of time. So, welcome to the first technical session, Fabrication. I'm Jian Kim from Texas A&M. I'm really honored to session this chair. Chair this session. So we are starting with 2 lightning talks and 6 exciting papers with small demos. So I'm gonna chase the time. Let's keep our attentions on.
Hi, I am Justin Moon, a third-year PhD student at KAIST Industrial Design, advised by Professor Andrea Bianchi. This year at UIST, I will be presenting shrink cells, a localizer sequential shape-changing actuations with selective heating. Shrink cells, we created a 3D printed heating mechanism that does not require external stimuli such as hot water. Also, we introduced 3D printed fuse that reroutes our current flow, allowing sequential actuations without any microcontrollers. It is part of my research vision of 3D printing electronics for functional and interactive prototypes. I believe 3D printing technology not only should allow complex geometries, but also interactive prototypes that can sense, actuate, and display. And I focus on controlling and programming 3D printed materials by selective heating for actuating, sensing, and processing. I would love to chat about my research and potential collaboration, so please feel free to reach me out.
Hi, I'm Faisal Matero, final year dual degree student at IIIT Delhi, India. I'm part of the Weave Lab, which is advised by Dr. Aman Barnawi. My research interests lie in AR/VR, tangible interactions, and fabrication. I'm particularly interested in the intersection of mixed reality and tangibles, and I aim to design for the perfect blend of the real world and the virtual world. This year, I worked on a couple of projects in this space while interning at iLab, University of Calgary, under the guidance of Dr. Ryu Suzuki. I worked on sketch reality, which will be presented at UIST this year. Sketch reality introduces this concept of bidirectional sketching, which enables virtual sketches and physical objects to affect each other. This year, I'm attending UIST as an SV, and I look forward to meeting the community and finding potential mentors as I'm seeking PhD opportunities starting fall 23.
All right, let's send our applause to the lightning talk speakers. We are starting by the first talk by Chao Fang. While setting up his. Presentation is going to present flaticulation laser cutting joints with articulated angles on behalf of his team at National Taiwan University.
Hello, I am Chao and I'll be presenting flaticulation. This is done with my colleagues Vivian and Longpan when I was in National Taiwan University. Flaticulation is a method to laser cut joints that clutch to cut in place boards at designated articulated angles. This allows fast assembly of laser cut 3D objects, simply folding cut pieces till they clutch. Our motivation is to quickly fabricate complex objects. Laser cutters are great in this case. It fabricates much faster than 3D printers, but since it cuts in 2D, extra effort is required when making 3-dimensional objects. Joints are necessary when forming 3D objects using laser cutters, which requires additional modeling effort. Hands-on assembly is also required afterwards. Previous work have provided interface to embed joints into design, or direct conversion from 3D models into various laser cuttable plans, such as using cubes as basic building units, or planar cross-sections with mesh joineries, and lamination for building mechanisms. Nesting laser cut pieces have been proposed for faster hands-on assembly. However, most joints connect well only when boards are perpendicular. This makes it difficult to fabricate complex polyhedral objects, requiring clamps or adhesive to assemble before holding the supporting parts. In the meantime, these joints cannot be cut in place. In other words, the connecting pieces have to be laid out separately to account for the laser cutting curve for a tight fit. Flaticulation introduced new joint patterns. The joint clutches two cut-in-place pieces at predefined articulated angle by just folding them. This enables easier way to assemble unfolded 3D polyhedral models and also add detent hinges into laser cut objects. Here is the workflow of making a computer mouse in flaticulation. The user starts with a low poly model of a mouse in a 3D modeling software. Once our user face in Rhino then inputs the 3D mesh and unfolds it automatically. Parameters, the joint patterns corresponding to the angles would be added to the unfolded pattern. And parameters such as the laser cutting curve and the material thickness can be adjusted in our user interface. We then locate the mouse button of the mouse button location and to add a detent hinge. The detent hinge would provide tactile feedback when the button clicks. Detent hinges can be added through our user interface by selecting the segments. The user then adjusts the angle of detent and stiffness parameters to tune the tactile feeling of the mouse clicks in our user interface. Finally, the mouse can be laser cut and assembled easily by simply folding pieces to clutch at the correct angles. We demonstrate flaticulation with various two-manifold models by unfolding the 3D models automatically, such as a wolf hat and a Stanford bunny. The models are assembled by folding every laser cut pieces. Non-manifold model can be also designed directly using our interface in 2D. Here we made origami-inspired crane and a boat. With detent hinges from flaticulation, we also built functional objects that have reconfigurable structures. I will now introduce the special laser cut patterns in detail. Two kinds of patterns, which we call T patterns due to its shape, is the foundation of flaticulation. The less than theta T pattern only allows motion with angles less than theta, which is in this range. And the greater than theta T pattern has a snap fit mechanism, and it only allows motion with angles greater than theta, which is in this region. The intersect of the range of motions between these two patterns will be exactly the desired angle. An articulated joint is therefore achieved by placing a less than theta pattern next to a greater than theta pattern. Let's have a close look at the patterns in action. Here you can see the two patterns. The greater than theta pattern in the right snaps, and the less than theta T pattern in the left limits further movements. So the two patterns work in unison to clutch the boards correctly. Besides articulated joints, flaticulation also makes detent hinges using a laser cutter by lining a greater than theta T pattern with a living hinge. This clip shows the detent hinge working, and the force here you can see there's a detent force when the hinge moves to the specific angle. Next, I will talk about the geometry of the cut-in-place T patterns that enables flaticulation. The patterns create a latch to be jammed with the material thickness. This is the cross-sectional view of the patterns to get a better idea of the joint, and I'll introduce them separately. First, we'll look at the less than theta T pattern closely. Here you can see the geometry, and the moving gray boxes indicates the range of motion of this pattern. And the the green dot over here limits the motion with the collision of to the gray boxes. So therefore, the position of the green dot determines the theta angle of the pattern. And we get the position by solving the intersection of these two lines. Next, let's look at the greater than theta pattern. Here you can see the head of the pattern first snaps, then rests on the top surface of the board. The position of the green dot will be the final laser cut position. But to get the position of this green dot, but to get the position, we need to look at the orange triangle first. And we can get the orange dot's position with trigonometry. Then the green dot is extended out from the orange dot to achieve the desired snap. We also looked into the effects of the curve of the laser cutter. We found out that this should be also considered when calculating the geometry. The laser cut curve creates small errors on the T patterns, like these areas. We therefore look into these and consideration in the geometry, and the details could be found in our paper. We performed experiments to evaluate flaticulation joints, in particular, testing angular error and the strength of joints. We tested 5 different angles with a total of 100 samples, and the average error is around 3 degrees, which is acceptable in our cases. To examine the strength, we first conducted simulation using finite element analysis. We simulated the joint under load of 2 directions, being pushed down and being pulled up. We identified the location where the maximum stress occurs, and the actual failure point matches the simulation results, and these parts should be strengthened for making stronger joints. We also tested different configurations of the joint in simulation. Using joints on a thicker material results in better strength, and widening the pattern also have similar benefits. Finally, we mounted the joints on the tensile testing bench and put torsional load on the joints to test its strength. We tested with 16 different joint angles and compared the results. We plotted the maximum stress of each joint, and the blue line indicates the joint being on push load, and the orange line is the joint under pull load. The joint should withstand at least 1.5 Newton centimeter of torque from our empirical testing. So here you see the joints with the angle in the range of 0 to 15 degrees and 90 to 103 degrees are weaker than that. So these are less useful. But for the other joint, it worked well and withstanded loads up to 34 Newton centimeter. Here I will talk about some findings and limitation of flaticulation. In our experience, repeating the pattern gives a stronger joint. However, we did not successfully run simulation in finite element analysis on repeating patterns to confirm this. So more tests would be needed to optimize flaticulation joints in the future. We also observed that the strength of the T pattern is not symmetric. Like it's weaker here but stronger in the middle. So this hints that arranging the pattern might lead to better strength of the joint, and it seems to be the case in our preliminary experiments. And speaking of folding sequence, most models can be folded in any order. However, some convex models like this one encounter obstruction because of the folding sequence. So this can be resolved by unfolding a joint and inserting the obstructed pieces, then folding the whole thing back. And this process could be automated in the future by searching the collision in simulation automatically and giving users instructions on the feasible folding sequences. In conclusion, we propose flaticulation and articulated joints that make fabricating complex structures using laser cutters easy. We presented a user interface and analyzed the geometry and validated our technique with experiments and demonstrated various examples. thank you for the listening, and please join us in the demo booth tonight.
Okay, let's thank our speaker. If there are any questions from the audiences. If you have any questions, please stand up here and then introduce who you are from where you are so that we can know who you are.
Okay, thanks for the very interesting work. I'm Sunjun Kim from Digit South Korea. And Digit, my question is, did you test the effect of the various materials? So relationship between the materials and the strengths, the functionalities.
Yeah, so we also tested out on acrylic, and it has slightly stronger strength, but it's more brittle, so it breaks really easily. So we did most of our prototyping on medium density fiber boards. Yeah.
So do you have any optimal material recommendation?
We think that the MDFs works quite well in our cases. Yeah.
Thanks.
Hi, I'm Koya from the University of Tokyo, and first of all, congratulations. And I
Thank
have
you.
several questions. So first of all, what is the maximum folding angle, and is it restricted to the thickness, for example?
The maximum folding angle we did like 160 degrees, like folding for 160 degrees, and I think it can go even further, but the problem would be the joint would be very long. Yeah, but we can get that angle.
Is it related to the thickness of the material?
Yes, also thicker material would have longer patterns.
And another question is, I'm curious, why don't you try more patterns like Mira-Ori or water-bound patterns, which has a low degree of freedoms? Most of the twist pattern is like a lot of single hinges connected together, but in reality, there are many origami patterns which has the dependent hinges with each other, with internal vertices inside. So did you try such kind of origami patterns?
No, we haven't tried them, but I think it would be really interesting, and also with the D10 hinges, that would be quite interesting, I think. Yeah.
Thank you.
Okay, let's thank our speaker again.
Thank you.
Our next speaker is Martin Neisser, who will be presenting Mixel's fabricating interfaces using programmable magnetic pixels on behalf of his collaboration at MIT CISL and U of Calgary.
Great, thank you. Good morning. My name is Martin Neisser. I'm a PhD student at MIT, and on behalf of my co-authors, I'll be presenting a project we call Mixels, which is about fabricating interfaces using programmable magnetic pixels. So magnets are embedded in objects all around us, and from tool racks to charging connectors to cabinet doors. And that's because they provide a powerful yet power-free way of actuating and assembling objects and imbuing them with interactivity. But those of you who have played around with magnets will know that rarely do you find more than one magnet or two in any given object at any given time. And you know why? It's because they bond together unpredictably and unselectively. And they will show you no mercy when you try to eventually pry them apart from each other. So as a key part of this work, we developed magnetic signatures that can be programmed into magnetic sheets, which when bonded onto objects, will let them attach rigidly in one configuration, but then become agnostic to each other in other configurations, including both translations and rotations. So we built a web tool to design these configurations, these signatures, and a magnetic plotter to encode them into magnetic sheet, which when applied to objects will make them selectively attract each other. And we explore a variety of applications to use this method to imbue objects with interactivity. So we built an inexpensive magnetic plotter comprised of an electromagnet to program magnetic sheet and a Hall effect sensor to read them back again. And we use a web tool for users to be able to design arbitrary 2D pixel patterns. So these pixel patterns can be designed as arbitrary 2D grids, as matrices, or they can use baked-in algorithms in the tool to automatically generate these selectively attractive magnetic signatures. And we use this pipeline to explore a variety of initial applications, from selectively paired objects to guided assembly. So in one case, we use a set of 3D printed tokens that are identical in appearance, material, and mass, but with magnetic signatures underneath, which let them be identified by unique force profiles when mated with another magnetic signature. In this case, lighting up a corresponding LED on the right. We can also create unique lock key pairs where using handheld keys on the right will only unlock particular associated locks on the left. So these keys are force generating, so they require no electronics or force transducers. They're reprogrammable, so you can update their access. And unlike physical keys, their structure is invisible to the naked eye. We could also program these signatures to guide with assembly processes. So these blocks are programmed such that they can only bond together to achieve a particular target shape. And we can use magnetic viewing film to display simple program textures as well. We can also program simple information into these sheets, such as QR codes, which can also be programmed to provide tactile displays, so to be selectively repulsive and attractive locally to another magnetic interface. So we use a soft magnetic material, which we program, and bond this to 3D printed objects. And we program this material pixel-wise to create these signatures. So these signatures can be cast as matrices populated with 1s and -1s, where a 1 corresponds to a north-aligned magnetic pixel, and a -1 to a south-aligned. And we can display this using yellow and blue pixels, like in this image. And so our goal with this project is to create, say if you have a number of objects and you want to coat them all with magnetic sheet. Our goal is to be able to create and program magnetic sheets that are selectively only in pairs. And so suppose you have 2 objects and you want them to mate or bond to each other only in a particular configuration on 2 different faces. Let's call these faces A and A prime. In this case, you want these 2 faces to be complements of each other. So wherever A has a north pixel, you want A prime to have a south pixel. So that way, when you overlap these matrices, they will be attractive at every pixel. And the same is true for all your other pairs in the set. So we can describe these selectivity requirements as a local rule and a global rule. So for this local rule, we want these 2 faces, A and A prime, to bond rigidly in one configuration. But then when we change the configuration, if we translate them pixel-wise or rotate them, we want it to become agnostic to each other, so they don't assemble in a wrong configuration. And equally for this global rule, it's simply put the fact that we want neither of these faces, A and A prime, to bond to any other faces in the set, so any other magnetic signatures that we generate. So to construct these matrices, we recursively generate Hadamard matrices based on orthonormal codes. So these are matrices that are row orthogonal and column orthogonal. And intuitively, what happens is when you begin to translate these matrices or rotate them, the attractive pixels and the repulsive pixels all add up to cancel each other out. And that's what generates this agnosticism. So once we've generated these Hadamard matrices, we then generate all 8 factorial row permutations, and then cross-correlate all of these matrices with each other and rank them in attractiveness across all translations and rotations. We then use a modified algorithm from a paper from Braun and Kerbosch to iteratively search for maximal cliques. From among these, we select our mutually compatible matrices, a sample of which you see here. And for now, we only use 8x8 matrices. So to kind of give you an intuition for this resulting agnosticism, these 2 graphs show the cross-correlation between 2 of these matrices as we slide them across each other and compute the attractiveness and repulsiveness between them. So on the x and y axis, you see the cross-correlation, or the correlation in x and y. And in the z-axis, you see the normalized force between 2 faces as we slide them across each other. So the normalized force ranges from +1, which is for 2 faces to be perfectly repulsive at every pixel, down to -1, which is when 2 faces are perfectly attractive at every pixel. So 0 implies this agnosticism, where all the attractive and repulsive pixels cancel out. So on the right, you see a figure that describes the cross-correlation for 2 signatures that should not mate in any configuration. And so you see that the forces between them are normalized around 0. They're bounded across 0 to be agnostic to each other. Whereas on the left, you see two faces that should mate with each other. And you see this sharp peak in the middle of the curve, centered on 0, 0, where the faces rigidly bond to each other but are otherwise agnostic. So to automate plotting of these signatures, we built this magnetic plotter that houses principally this electromagnet that can program these signatures pixel-wise. And so we built a hardware add-on that cost $62 worth in parts and affixed it to a 3-axis CNC. And this add-on houses an electromagnet which can program these magnetic pixels bidirectionally. So it can program both north and south aligned magnetic pixels. And we use a Hall effect sensor to be able to read these magnetic signatures back into the program. And both of these components are adhered to the hardware add-on using spring-loaded pogo pins in order to give the system compliance as it goes through these plotting procedures. And we use an H-bridge to control the electromagnet, which is what allows us to control it, to energize it bidirectionally. This is what gives us the capability to program both north and south pixels. And we case all this in a 3D printed housing together with an Arduino to do control. So once plotted, we can read these signatures back, as I mentioned, using this Hall effect sensor. And then we can replot the same magnetic sheets with the new programs. And this prevents us from discarding previously used sheets and instead lets us use them for new applications. So here you see a normalized Hadamard matrix, which has been read and then reprogrammed as a simple checkerboard pattern. So we developed a web tool to support the design and visualization of these signatures, and which also converts signatures generated automatically into G-code for plotting. And it supports design in 3 different modes. So in the first mode, users can generate just arbitrary custom 2D pixel patterns. So here a user is generating a simple checkerboard. And on hitting the export button at the bottom, it'll automatically generate the G-code required for plotting. We can also upload previously plotted programs that have been scanned in order to discover or copy or edit previously used programs for new purposes. And we can also rapidly generate pairs of these selectively attractive or repulsive magnetic interfaces to generate the kind of applications we saw earlier. And we can also generate large interfaces where we can ascribe selectively repulsive or attractive or agnostic pixels across the sheet. And so we showed that we can accurately program, read, and reprogram these magnetic interfaces. However, the pixel strength is currently limited to around 1.7 kilopascals, which corresponds to around 100 grams per square inch. But by substituting out this inexpensive commercial magnetic sheet that we've been using for materials that are capable of holding greater flux densities, we believe we can rapidly increase this strength. And the plotting speed is currently restricted to about 0.5 pixels per second. But we think that by substituting a single electromagnet with an array or a grid of them, we can parallelize this plotting and rapidly increase the plotting speed too. As for the matrix size, we're currently set at an 8x8 grid. And going down in size will compromise selectivity. But equally, by going up in size, we think we can rapidly get more selectivity if we can decrease the pixel size. And what we talked today a little bit about near-term applications, one future application in the longer term that we're excited about is self-assembly. So this idea that we can use self-assembly to acquire a target structure without any human intervention. And we recently showed that we can program with magnetic signatures 8 cubic modules and have them self-assemble stochastically without any human intervention in type order. And with some partners from NASA, we've deployed 150 of these cubes programmed, which will, in a few seconds, self-organize into 2 different cohorts, so blue and yellow cubes. And we hope that in the future, this can offset cognitive loads for assembly tasks in orbit. So in summary, we looked at how magnets are embedded all around us, but how they're unselective. And we showed that we can generate magnetic signatures that make objects attract each other in one configuration, but become agnostic in others. And we showed that we can build a fabrication pipeline using a magnetic plotter and a web tool to design these signatures, program the multimagnetic sheet and develop a variety of application use cases from selective key unlock pairs to guided assembly. Thank you.
Questions from audience?
Hi, this is Andrea Bianchi from UIST. Thank you for the talk. I was just curious, if you take a magnet that's relatively strong and you put it next to these polymagnets, do you basically erase the pattern you just generated, the signature? And if that's the case, how do you think this is a limitation for the type of application you're doing? Because maybe you have something encoded and suddenly you just completely erase it.
Yeah, that's a great question. Yeah, so all of these soft magnetic materials, so the softness of a magnetic material basically tells you what strength of external magnetic fields is required to reprogram it. So even like a strong permanent magnet that you correctly imply could erase these are themselves programmed with stronger magnetic fields. So I think the answer to your question is it becomes a problem of choosing a material that can be programmed easily enough using a weak magnet, but won't be reprogrammed accidentally by another stronger magnet. But you can set that threshold by choice.
Thank you.
Hi, Zoe from University of Maryland. Nice talk and cool mechanism. I was wondering, because you're presenting one of the potential application on security with like you can program different patterns and so that you have like different tokens for them. I guess I was guessing like your sensor sheet is going to be pretty available as well. So at the same time, it's like if I as an outsider, if I just use that to visualize like what is actually in your access, and then I can easily reverse engineer a token to open that. Like, is there any physical mechanisms you thought about to tackle that?
Yeah, it's a great question. We haven't thought too much about the longer-term implications for security, but you're correct. You can view these patterns using magnetic viewing film, so just by hand, but that doesn't tell you the actual magnetic poles. So you see, it just tells you where you have a change from like a north pole to a south pole. It also doesn't tell you anything much about the continuous strength of the field. So we've shown as well that by changing the field strength of the electromagnet in a continuous manner, we can achieve much more diversity in these programs. So maybe that's a way to kind of reconcile that problem.
We'll have one more question.
Okay, the last one. Okay, my question is about the material, the magnet. I mean, this material seems very soft or rigid. I mean, if it's very soft, we can create some the shape changing interface with this magnet pixel. So, can you introduce more about this material?
Yeah. So you're exactly correct. One of the reasons we chose this material in particular was because it's easily programmed, but it also is a little bit flexible.
Yeah.
So we were exploring early applications using kind of continuously deformable substrates. These materials comes in many different shapes and forms. You can even make them yourself by like casting like iron particulate into like a silicon matrix. So you can get them with flexible and rigid substrates for sure.
Okay, thank you.
Thank you.
Yeah, let's thank our speaker again. Our next presenters are Zachary and Carlos, co-presenting L-Logic, embedding pneumatic computation and I/O in 3D models to fabricate electronics-free interactive objects. For the audiences who are watching the YouTube video stream, you can also post your questions to Discourse, so please do so.
Thank you for that introduction. I'm Carlos, this is Valkyrie. We're very thrilled here to be on behalf of our collaborators to talk a little bit about L-Logic. So as most of us know, physical interfaces have some intrinsic benefits about the screen-based ones, like virtuosity or ice freeze control, which is why artists and professionals prefer them over screen-based applications. However, creating these interfaces is not trivial. Sometimes it requires assembly of parts, soldering of circuits, or even training machine learning models. So it's inspired by these limitations that we started working on L-Logic. L-Logic is a system that embeds I/O and computation into 3D printed objects using fluidics. These objects are produced as a single structure with very minimal assembly. But what's fluidics? Fluidics is a technology that was developed between the 60s and 70s, and 80s, sorry. that relied on interacting jets of air to perform computation, some from logic gate to volatile storage. And the reason that it makes a great substrate for tangible interfaces is that we can produce these interfaces both in form and function using a single process and a single machine. These devices that are produced with this have input, logic processing, and output embedded into the actual device. Another thing, and this is super cool, is that because the devices itself are stateless, it means that they don't require any resetting in between uses. So how does it work? Air logic relies on printing custom geometries connected by tubes inside these models. We call these transits because, similarly to electronic transits, there's only one direction that you can go in them. So for example, on this bunny that is on screen now, there's a transit that can detect 2 input locations, and whether each of these are interacted with, it wiggles its tail. To take a closer look on how it works, let's do an X-ray on this bunny. Here we see that this transit has 2 input widgets, one OR logic widget and one wiggler widget. So what happens when we connect this with air? So the first thing that happens is that air just escapes the system from the 2 input widgets. When one of these are blocked, the air is routed back into the system into our OR widget. Here the analogy is that a presence of a jet of air is a binary 1 and an absence of a jet of air is a binary 0. So similarly to the OR gates that we know for computation, we get a 1, 0 input, which gives us a 1 output. So this output is also a jet of air that we use then to move the tail of our bunny. But of course, our logic is more than making some super cool bunnies. We developed 15 different widgets to create tangible devices. So starting with input, we wanted a structure that could detect a binary 1 or a jet of air when it was touched. So we developed this structure that was similar to an inverted T-shape. So the air escapes when it's not blocked, but when it's blocked, it just reroutes it back into the system. The cool thing about this design is that since it doesn't rely on any resistive or capacitive changes, just a blocking of an outlet, we can just block that with something different than our fingers, right? So if we create some spring-like structures and a plastic top, we have a button. We can also create a rocker switch that one side blocks it and the other one lets the air through. These input widgets can also be we can also have multiple channels for these input widgets. So if we arrange them in parallel and use a handle to block them, we made a slider. And similarly, if we arrange them in a circle, and we just contrast with a dial. So another type of widgets that we have are logic widgets. Here, like I said before, the analogy is that a jet of air is a 1 and an absence is a 0. These logic widgets are based on the principle of jet deflection, which tells us that a jet of air can be redirected if hit by another jet of air at a right angle. So we use this for calculation then. So if we send a jet of air through to one of our structures, it just goes through as we expect. Similarly to the other side. But when we input both of them, they collide and their momentum gets canceled out. So it outputs for a different channel. So this is what we use to make our logic widgets and to make all the calculations in our gates. So that example that I previously mentioned is our AND gate. So here, when we have 2 of our inputs, we can sample the middle channel and we get a 1, which is another jet of air. Our XOR gate has a similar design to our AND gate, but here we sample a different channel. So we instead vent the channel where both inputs are present, and we only sample the one that has 1 input present. Also, our NOT gate use a similar design, but here we have a steady power that we denote here as P. So here we sample the top channel, and then we vent the last 2. So when the input A is present, we get nothing on top, but when it's not, we get a 1. And finally, our last widget is our last logic widget is our OR widget, which is our simplest one that performs basically as a Y merge. So here, if any input is present, it just continues through the transit. So now Valkyrie is going to talk to you guys about some output widgets and some more cool stuff.
So, whoa, I'm skipping all my slides here. So as the final part in our transits, of course, we have to give output to the user in one form or another. We developed some visual widgets, some haptic widgets, and some audio widgets that all use air for their output. So the first one, as you got a minor preview of, is the pin popper. It basically relies on a stream of air to push the pin up. We also have a whistle, which makes a tunable sound with a fipple and a resonance chamber when there's a 1 present on the transit. The oscillator is similar to the pin popper, but instead of going up and staying there, it can wiggle as the stream of air pushes it down, and then it returns to its original position due to its weight. And finally, the haptic output we designed is this vibration motor, which pushes a wheel inside a chamber to basically vibrate the device. To make it easy to experiment with our widgets, we developed a Fusion 360 plugin that enables adding encapsulated versions of the widgets as well as unencapsulated versions, which, by the way, we did release on this GitHub, so you're welcome to play with AirLogic as well. So for prototyping, designers can print encapsulated widgets, which are essentially our widgets in little boxes. And these can be connected with off-the-shelf tubing so that designers can prototype their transits and see that they work how they want. When they're happy with that design, then they can take the unencapsulated widgets, which are just the bare pipes, and move them around in their model and cut them out so that they have a final object. Then, of course, the device can be printed with all of these widgets integrated. We performed a series of experiments to understand how well our widgets worked, in particular, how much airflow each type of widget loses, as well as how they're affected by printed tube radius and the orientation of the gates inside of our printer. There's more details in the paper, but the sort of TLDR is that widgets all preserve airflow better at lower air speeds. Bigger curves are better, maybe not a surprise, and the relationship between airflow and printing orientation is a little bit complicated due to the ridges in the FDM process. We also, of course, built a series of example objects to show off what AirLogic can do. So in addition to the bunny that Carlos showed you, we built this block puzzle where if users correctly spell the word UIST, we pop up a pin. This uses encapsulated widgets as opposed to doing a single large print, which saved us multiple days of printing time. We also built a lung-powered pitch slider that shows off how our devices can work without an air compressor. I'm short on time, but there are more examples in our paper. Onwards. One challenge when we're relying on air is turbulence. So historical fluaric systems and AirLogic both work best when the airflow is laminar, which is the flow that you see at the top. If laminar flow is disrupted, like in the bottom picture, then it can impact our system's ability to calculate correctly. But we can mitigate this by choosing appropriate air pressures for the system. Also for now, because of this jet deflection mechanism, our designs rely on having balanced amounts of airflow for our and or gates to work. So if the top flow is stronger than the bottom flow, then instead of hitting and coming out straight, they'll sort of go in a different direction and our computation will be off. However, historical fluaric gates used amplifiers to overcome this limitation, so we think it's possible for AirLogic too. When we compare AirLogic with electronic prototyping kits, we have some important drawbacks for now. So we don't have timers, we don't have storage, our sensing is fairly limited, but we also acknowledge that an air compressor is not quite as convenient as a battery for the moment, although there are portable sources of pressurized air like your lungs, the wind, or CO2 canisters. We also have some unique capabilities relative to electronics. So AirLogic can be great when traditional electronics would get wet or irradiated, or if electrical power might be hard to come by, such as in a remote area of a national park. We also have an advantage over what Carlos showed at the beginning, this sort of assembly of electronics and plastic. So our devices are in some sense more sustainable. They're all a single material, so when you decide you don't like your device anymore, you can just chuck the whole thing into recycling. We're also interested in trying out other ways of fabricating AirLogic devices. Here we tried laser stacking to recreate a traditional historic gate structure on our laser cutter. Also, if any of you have read our keynote speaker's short story Exhalation, we're really interested in how AirLogic is essentially a part of those mechanical air-powered beings. So Carlos and I have presented AirLogic, which is a technique to fabricate 3D printed objects with integrated air-powered sensing, computation, and output. We discussed 13 pneumatic widgets that demonstrate the basic technique. We also highlighted through measurement the opportunities and challenges of our widget designs as fabricated on consumer 3D printers, And we demonstrated their use in interactive objects that don't require any electronics or coding. We think our work moves towards the vision of instantly interactive, single-pass printed objects decoupled from external computing devices. We're delighted to be here presenting on behalf of all of our co-authors and happy to take questions. We actually didn't use anything special to make these devices. These are just printed like exactly how they come off of your basic FDM printer. Airtightness is not that big of an issue because it's more about like the airflow and direction in this case.
Yeah, so AirLogic devices are not pressurized at all. So it's just creating like ridges for the air to flow through. I did some previous work that I actually pressurized the device, and I also had problems getting it to work with FDM. You can try increasing like wall thickness and on the mesh on the inside. Maybe could be a bit helpful.
Yeah, thank you.
Yeah.
Hey, I'm Shohei Katagura from Hasselblad Institute. So my question is this just a small curiosity. So because a lot of holes and also some cavity inside a 3D printed object, how did you print such type of object, and also how support material affect the interaction, support and quality of the inside of the surface? How much affect these interaction for the
We actually, the way that the gates are designed right now, they don't require support material inside.
How did you print it?
What do you mean?
So because the hole inside.
Yeah, well, so for overhangs of like over 45 degrees, normally you do need support, but in this case, because it's a cylinder, you actually don't need support for that. So these have no internal support material.
Okay.
Hi, Jasper from the University of Washington. Found this super cool. You mentioned, I guess, more traditional fluorics that you may not have caught on. I hadn't heard of them before. And so given that you have this pipeline in 3D printing, just curious, what do you think, how might this potentially make fluorics more popular or not? Like how would this improve over kind of like the classical phase of fluorics?
You want this one?
Sure. So one of the main issues with the fluorics in the past is that they were a bit vague, so they didn't have a lot of measurements and stuff. So we hope that by kind of formalizing this a little bit, we can give some guidelines on how to do these structures, focusing on 3D printing. So like we cannot say that our measurements and our sizes would work if you would do the chemical etching and all the stuff that they did in the past. But in our paper, we provide like the sizes for our tubes and our cavities and all of our stuff. So we hope that would just get the ball rolling too for the future.
I would also say that the other thing is that fluorics was abandoned like in the early 80s, which was when we started having like really interesting input devices. So essentially classical fluorics really only demonstrates like essentially the touch sensor that we show here. They also have like something closer to like a presence sensor where you can sense something that's a distance away. But I think that there's a lot of like rich opportunity for like how we can design new kinds of input with this.
You have one more quick question.
Oh, thank you. So just a clarification. So Andrea from KAIST. You say you don't have storage, but you have XOR, you have AND, you have NOT. You could do a flip-flop. Have you tried something like that to actually build up a logic storage inside of your system by combining them together?
We haven't. So I'll say that the traditional fluoric devices actually did storage with jet sticking. So basically, if you have a cone, you can direct the jet to stick on one side, and then it'll keep flowing on that side versus you deflect it to the other side and it stays there. But no, you're right. We could chain these in some way to make storage happen. We just haven't done that.
Thank you.
I did not use the force to make any of these devices work, just as a clarification.
Okay, let's give a round of applause to the presenters.
All right. Hi, everyone. My name is Abdullah. I'm a PhD student at the Hasselblatter Institute, and this is Hinge Core. So as you see from the video, we're going to be presenting a fabrication technique that allows you to quickly fabricate 3D models. And our objective was to enable very fast prototyping. So the idea was to get from idea to assembled prototype in less than 15 minutes. And the key goal was to enable multiple rounds of prototyping, say during a meeting or whenever you're hanging out. And to tackle this challenge, we focused on laser cutting. So I think all of us know that laser cutting, the tech itself, is very fast. So the chair model you just saw, it took about 3 minutes to laser cut it. Modeling traditionally used to take a long time. But after 3D modeling software such as FlatFit Fab and Cube, this time was condensed down considerably as well. So this leaves the last part in the pipeline, which is assembly. And as we see that this now dominates prototyping speed. And after having figured this out, we decided to speed this process up specifically so we can speed up the whole pipeline. Looking a little bit deeper, we see that there are actually two subparts. One is searching for plates, and the other one is joining them. And at last WIST with Roadkill, we tackled the plate search sort of problem. And this time around, we're trying to figure out how to speed up the joining of plates with Hinge Core. So I'll give you a quick recap of how Roadkill tackled the plate search problem. So if you look at traditional laser cutting, the way we communicated to the user which parts belong where and how to search for them, we actually had lookup numbers engraved or printed on essentially on the edge of different parts. And the user would look these up and try to find the other corresponding part. Here they're looking for 19. And this used to take a long time. And if you dig a little bit deeper, what essentially plate search is a quadratic process. So as you start as you're at the beginning, you would take a long time because there's a lot of parts to find. And as you start to find more and more parts, you start to build your model, it will get considerably faster. So it's an n-squared process. Now, sadly, what we found is we can't get rid of the square here. But what we can do is substantially reduce n. And what Roadkill does is exactly that. It takes a bunch of parts and groups them into sub-assemblies. So rather than looking for individual parts, you'll then be looking for sub-assemblies. And within each group, we have in-plate assembly instructions, which eliminate essentially any kind of visual search. So here you'll see that the user is actually just picking up parts that are right next to each other, putting them into the corresponding part, which is also next to them. And occasionally they may follow an arrow or so. But once this group is complete, now they have to do a little bit of plate search. And the idea as well, in this case, instead of 23 parts that usually make up this chair model, it's down to 4. And this sped up the whole plate search process by quite a bit. And we found it's like grouping plates on average by 5 or so, which is what the Roadkill algorithm achieved. We're actually able to reduce this by 25 times, 5 squared. And now the other monster in the room is essentially joining plates. So this is now again the dominant term. So that's what we're going to talk about today with Hinge Core. And here's what a typical Hinge Core layout looks like. And the main idea is that we want to physically connect the parts within each subassembly. And this essentially results in what is called rigid origami. And you have rigid material, which are the plates, and you have the hinges in between them, which hold them together. And we fabricate this as a single integrated process using a material called foam core, which is a paper foam paper composite. It's rigid by default, but what we're able to do is by cutting halfway, we're able to produce a hinge in the material. And the key design element of Hinge Core is what we call a finger hinge. And it's a combination of a box joint and a standard hinge. And these finger hinges, they not only hold the parts together, but as you can see, they also allow you to fold the parts to assemble them. And the cool thing is, well, when you let go of them, they stay in place. And this holds true for the rest of the model. So if you fold the whole model together, at the end, you don't need any glue or tabs to keep it there. Oh, okay. Maybe there's some reverb here. So we conducted a user study okay. There's some kind of crosstalk happening. I really don't want to talk too much so that we don't have feedback. All right, so we conducted a user study to find out like how the new version of Hinge Core compares against pairwise numbers or Roadkill. And here's a quick snippet of how it went with our participants. So here's 4 of them, and you see at the top that they actually are able to assemble the model pretty quickly within less than 4 minutes or so. And the one person at the bottom takes about 6 minutes. And if you look at the data, The participants were on average 2.9 times faster than the in the hinge core condition compared to roadkill. And if you now compare it to the actual numbers, the average numbers for assembly for all of these different techniques, pairwise numbers was about 22 minutes. With roadkill, we reduced it by twice to 12 minutes. And with hinge core, we're actually able to take it down by a factor of another 3 to 4.25 minutes. So what this means is that in comparison to roadkill, hinge core accelerates the joining of plates by about 2.9 times. So just to summarize, hinge core enables fast assembly of laser cut models by grouping parts into sub-assemblies, which it inherits from roadkill. And it introduces self-holding hinges between parts, which is unique to hinge core. But in addition to speed, hinge core offers two additional qualities. So the first thing we notice that hinge core models are sturdy. So during this compression testing of the doll chair that you saw earlier, it's able to withstand 62 kilograms, and that's because it's made of rigid origami, essentially, solid plates, and box joints that are good at resisting compression and shearing. And this allows us to build functional, load-bearing models, such as guitar stands, stools, and robust toys. And the other quality is a clean look. Now, I think all of us have prototyped with laser cutting, and typically if you involve box joints into your fabrication process, they will be visible from the outside. But the cool thing about hinge core is, well, it hides them now, so you don't see any of the finger joints or the box joints as they're called, but rather they're hidden. And so we feel that this actually opens up this venue to people who might care about the aesthetics of their prototype, rather than say how the joinery method is enforced. So the focus is on the model rather than how it was fabricated. So this allows industrial designers perhaps to create speakers or lamps or sculptures or even architecture models potentially. And finally, hinge core can be painted. And this may not matter to us too much, but kids enjoy customizing their stuff. And they can assemble the model, they can paint it. And this goes well with the fact that hinge core requires less force to assemble than plywood, and requires less logistics skills. So they can, kids can actually put it together without making mistakes or, with the parts falling around and not being able to put them together. So the hinge core algorithm is actually, it can work standalone, but we also integrate it into Cube, which is the 3D modeling software that our lab showed back at KI 2019. And the idea here is that users pick the, so they basically apply the foam core material to their 3D model. Wait. Okay. So they double click the model, essentially applies the material, and at that point you can use any of the tools available within Cube to model however you want. And then when the user is ready to export their model to fabricate it, then the hinge core algorithm will actually automatically place hinges and the seams. And the algorithm that we built for this was custom. We created a heuristic-based algorithm that allows edge unfolding to happen on a variety of models. And for more details, you can look at our paper. So here's a rough outline of the cutting plan that the algorithm generates. And here's where it places the hinges to connect different parts. And here's the box joint geometry that creates the finger hinges essentially at the end. Here's a quick look at the cutting plan. So the red line here indicates cut through. So it tells the laser to cut through all 3 layers of the material. And then we have the blue line, which allows the laser to basically crease the hinges so it's easier for people to fold them. And then we have magenta, which cuts partially to create the box joint geometry. So one thing that's a little bit missing is we actually cannot remove this block of material by using the laser traditionally. This creates a bit of residue here. So, well, we tried getting rid of it with the laser by burning it off, and it took quite a bit of time. We then shifted to using tools and picking them out with our fingers, which we found was quite fun, fast, and also sometimes addictive. But what we ended up doing at the end was this fast method where we use heat shrink foam core, which actually shrinks away as heat is applied. So we actually create a bunch of more cut lines here that shrink away the material. And when the user assembles the model, it crushes all of the residue within the joint cavity. So here's a quick technical evaluation of our algorithm. So hinge core unfolds better than roadkill. That is, produces larger subassemblies with more parts. And we ran it on a bunch of standard models from the Cube repository. The average time to compute the layout was about 3 seconds, which does not add a lot of time to the export pipeline. If we look at the results, so here's the number of plates per model in the horizontal axis. Here the number of subassemblies on the vertical axis, and here's how the models are spread out in the terms of number of subassemblies that hinge core creates. And if you look at the trend line here, essentially means that the average subassembly size is 8 plates, which is 1.6 times faster, 1.6 times better than roadkill. But this is not all of the models. We also have some models that are beyond 200 plates, and the trend line almost consistently continues with that as well. So in conclusion, our objective was to enable very fast assembly, to have an idea to an assembled prototype within less than 15 minutes. And the key thing was to be fast enough to do multiple rounds of prototyping, say during a meeting or other event. And now as you look at the pipeline, we identified assembly as the bottleneck here. And there were 2 key parts. First, we solved the plate search part with roadkill, and then we tackled the joining parts with hinge core here. And eventually, as you see, roadkill is able to group plates together into subassemblies to reduce the visual search part, while hinge core essentially takes care of joining plates and accelerates that by 2.9 times. So at the end, when you look at their combined effect, we take the assembly down from 22 minutes from pairwise numbers for the chair model down to 4.25 minutes. And the key thing here is to notice that, well, now they're all in the same ballpark. So it's not like a different time scale for assembly, but rather it's within the same time scale as modeling and cutting. Because we believe that designing this chair takes less than 5 minutes. Laser cutting this chair took less than 5 minutes too. Well, maybe assembling should also take less than 5 minutes to get to a quick fabrication pipeline. So this makes hinge core and roadkill steps towards rapid prototyping, or what we call 15-minute prototyping. And I would like to thank my co-authors here, especially my supervisor, Professor Patrick Bodish, for his help and guidance throughout my research. And before I let you go, I'd like to remind that we're also demoing a hinge core today, and if you want to have fun assembling these models yourself, picking out the parts and so on, feel free to swing by. And we're also an extra treat. If you can identify what this model is, what this layout turns into, we're also giving a bunch of these away at the booth, so you can take them with you if you want. All right, thanks a lot, and take your questions.
We have the time for questions.
Thank you for your talk. Thank you for your talk. I'm Koya from the University of Tokyo, and I have a question. Is it possible to achieve both mountain and valley folds?
Yes. Yeah, so maybe you didn't see this here, but so valley folds are also achievable. The only problem is we don't have box joints in them. So they're more like a standard hinge, so you would just basically cut through and you can fold it the other way around. There's no encoding of, say, the joint angle in that case. So the other joints, they have an encoded angle based on the length of the fingers.
Yeah.
But in case of...
Another quick question. Is it possible to achieve the angle less than 90 degrees?
Oh, yes, yeah, sure. Yeah, I mean, so if you look at the example models here, there's a bunch of, for example, the unicorn, there are different angles, obtuse angles and also acute angles. If you look at the guitar stand, there's a bunch in there too. The stool has some of them. But you can also swing by the demo and you can create models yourself, and you'll see how the layout looks like for angles less than 90 degrees.
Yeah, thank you.
Yeah.
Hi, I'm Shu Hong from Julian University. I think it's a very effective and helpful way for users to assemble their own stuff and objects. And I noticed that they are all static. And I wonder maybe we can combine some origami and kirigami structures to make some flexible hinges, and therefore we can add some movement and build some dynamic things by using this assemble method. What do you think of it?
No, I think it's a wonderful idea. We did one quick little prototype in the lab where we had a bistable structure made with this, and I think I love the suggestion. Maybe we should talk as well at the demo or so, just to see where this could go. Yeah, I love it. Yeah, thanks.
Jasper from the University of Washington. Cool talk. I was curious about the environmental aspects and sustainability and impact of foam core, and what you have thought about that.
Right. Yeah. So we also did the same process with cardboard essentially, and you see that cardboard is also a composite, so it has the packaging material essentially. You have card paper at the top, and you have a corrugated structure in between. And sadly, I forgot to bring one of those things to the demo, but you can basically do the same thing there as well. Now it's a little bit less sturdy. We didn't do too many tests there, but it can also be used to fabricate in the same way.
I meant like the environmental impact.
Well, I would suggest that maybe in this case, if you're worried about the environmental impact, maybe we should go with, say, paper folding that involves cardboard or something that can be recycled. Essentially, you take your packaging, you throw it in the laser cutter, you make a prototype out of it, and then you hand it back, it gets recycled again, and so on. So foam core itself, I wouldn't deal with that sustainability somehow, but the technique itself, you can apply it to other composites that are 3-layer essentially. Yeah.
We'll have the last question.
How accessible is this foam material, and how much does it cost, or is it really costly to produce any prototypes?
So it depends on which of the brands you pick, but essentially we're using polyurethane here. This is about, so I can't say exactly. I mean, I can check it up for you. I don't remember exactly the numbers, but we never found it too expensive. And the other cool thing is, well, as I told Jasper here, you can use other composites. You can also make your own. You can use cardboard, which is freely available as well. So the technique works effectively for all of these, for sort of not all, but a combination of 3-layer composites where you have a sort of a solid layer in between and paper layers that can be cut easily to create hinges on the top and bottom. Yeah. Thanks.
I'd love to give another round for the He will be presenting iWood, Makeable Vibration Sensor for Interactive Plywood, on behalf of his collaboration at Dartmouth and Simon Fraser. His fifth-year PhD students on the job market. If you are hiring, you know who to contact for the rising star.
So yeah, hello everyone. Thank you for the introduction. So yeah, I'm Dian. So I'm a PhD candidate from Dartmouth College, and this is my last year, and my advisor is Xindong Yang. So today I'm very pleased to talk about a new type of interactive material called iWood, which can be easy to use to create smart environments. So this interactive plywood is made of plywood material, and it can sense the vibrations to recognize user gesture and activity. But before diving into the detail of this project, I would like to quickly show you what iWood looks like and what it can be used for. So this is iWood. So it looks and feels like the regular plywood you use for laser cutting or to use for furniture. And this plywood can be made as a smart table, and this smart table is capable to sense different activity like writing, erasing, or stapling, or pen sharpening. So in addition to the smart table, we can also use the iWood to make smart cutting boards. So yeah, so the vibration pattern will be shown on the laptop screen. So the cutting board can sense different kitchen activity, such as chopping, slicing, or stirring, rolling, grating, and tenderizing. So this smart cutting board can enable many different applications in the kitchen. For example, have you encountered a situation that the recipe video played too fast and you cannot follow it because you didn't have a last step and the video already go to the next step? So with these cutting boards, the video can automatically pause if it doesn't detect the user have completed the current process or current step. And in this example, the user didn't complete the meat tenderizing, so the video is paused. And after the user is finished the tenderizing, the video will automatically resume. Yeah, so it is iWood, and you may be curious right now how it works right now. So next I'm going to talk about more detail about its sensing principle and how it is made. So iWood is based on the structure of triple electric neural generator, which is a similar effect when you rub the baron with your hair, and your hair will be drawn to the barons. So it's a similar concept, and we built this structure in the wood, and it could convert the mechanical vibration into the electrical signal. So it is made of a layer of negative triple electric layer, such as PTFE film, which is quite expensive and very common materials. And it can be sandwiched with two layers of electrode, which are positive triple electrode layered. and each attached to the plywood substrate. So when a vibration occurs, the contact and the separation of the electrode and the negative triple electric layers will generate electricity due to the triple electric effect. And the next voltage signal is highly correlated to the vibration pattern. And so I will sense the user gesture or activity based on this vibration pattern. So right now I'm going to live demo how this plywood sensor works in real time. So, yeah. So you can see when I click it, it has some signal from this plywood sensor, right? And so this sensor is quite sensitive to the vibration I put. But please allow me to remind you again, our goal of this project is to make a smart environment using interactive material, right? And if you are the person using the such interactive material and you are going to create smart environment, what will you do on this material? I think most people will directly cut it, drill it, nail it, right? That's the natural human behavior with the material. So right now, here's the questions. Do you think it is a material we want? And to me, my answer is no, because it cannot withstand some working operation. For example, if I put a screw into it, please hold it well. So there's no more signal response. So this thing is not the material we want. And so in this project, we try to solve these problems. And the reason for the malfunction of the plywood sensor is that the screw will directly cause the short circuit between the two electrode layers. So there's no more signal response from this plywood. So to solve this problem, we redesigned the structure of triple electric nano generators. We stagger the top and the bottom electrode to put them into cover different parts of the sensing area. So this design can significantly reduce the short circuit issue. So right now I'm going to show the one we made in this work. So yeah, so again, let's see, pause. Oh yeah, there's a signal when I click it, right? And right now I'm going to put the screw inside. Yeah, I'm not performing Kung Fu, but yeah. Yeah, so it still works. So that's the material we want, and then we make in this project. Thank you, everyone. So yeah, and actually this project is not simple as you think. So we solve this problem. Actually, it also induced another problem related to the cuttings. So in high level, cutting will result in the different coverage of the top and bottom electrode, which will result in more noise in the signal, which lower the sensitivity. But here, so I don't want to talk about it in detail because it's quite complicated. If you're interested, you could take a look at our paper. But in short, we run the many simulation and experiment to get the best structure design to have the best sensitivity and also make this plywood capable to respond to the cutting and the screwing. So right now, the plywood sensor design is determined, and we fabricated this sensor. After this, we want to make multiple smart everyday objects using I/O. So people can conduct any worker operation on it. For example, a maker can drill it and screw it and sand it. So that's how the smart table I showed you earlier is made. And another example is the nightstand, which can also be made of I/wood. So I/wood can be cut, and it could be screwed into the other part of regular plywood. So here's the nightstand, and there's a demo for this nightstand. So it looks really a lot more like the one we use every day, right? Beside to the bed. And this nightstand can sense some common activity like pumping the lotion at the night, or you using the dispensing the tap. In addition to the top panel made of I/wood, the drawer could also be made of I/wood. So it can sense if the user takes something out from the storage and put something back. Furthermore, IWU can also be laser cut. So yeah, so the cutting board I showed you earlier is made by laser cuttings. So with this IWU, the cutting board can easily be made. So after making the the smart everyday object, then we build the data process pipeline, and we convert the vibration signal into a spectrogram, which is the frequency spectrums over the times. We extract the feature on the spectrogram and then put them into a random forest model to have a prediction result for gesture recognition and activity recognitions. For evaluation, we test 6 working activity, which we were showing in the videos. We test the working activity on the table and the nightstand, and we test the 6 kitchen activity on the table and the cutting board. So for specific the object made of iWood, the accuracy is really good. So with new accuracy, it's 95% average, and the cross-user accuracy is close to the 90% average. So it indicates that using this sensor to make the smart everyday object, it is still possible to allow the system to have accurately recognize the gesture and activity. And we also run mixed object accuracy, which means the cross-user accuracy by making all the data, by mixing all the data, which means the data from the nightstand, table, and the cutting boards, which you can gather 84%, which is in kind of encouraging result, because you can think about in the future there's a general model for such material, and you can recognize all the activity even though it is made to a different everyday object. And we also run the cross-object accuracy, and the cross-object accuracy means that we use the data from the table and we test the model on the data from the nightstand and the cutting board, which shows that the accuracy is quite low, but it makes sense because the model has to see the specific structure before. If we didn't see the structure before, it's really hard to get the model to recognize the gesture and activity. So yeah, in end of this talk, I would like to talk about makeability. So makeability is a new concept I introduced, I advocated in recent years. So it's an important property of interactive material. So what's the makeability? So makeability means the ability of interactive material remaining functional against the common fabrication operations, such as screwing and cutting I showed in the videos. And I think makeability is a key to democratize the interactive material, because the material can be now handled with the established method to create smart environment at larger scales. So in the new area of ubiquitous computing, the digital property of interactive material, such as sensing, could be inheritable, just like the natural property of the material, like stiffness, elasticity, they are the natural property inheritable to the object made of such material. So in this case, anything is made of IO capable to sense the vibrations. So when the furniture and the real artifact is done, then interactivity for this object is inherent. So yeah, so that's all I want to talk about today. And this project is open source. So if you're interested, you can take a look at this report. And yeah, this year I'm John Markey. Happy to take any questions. That's a good question.
Is it possible to apply this method to plastic or other materials?
I think the title just, I don't know, maybe I ask my advisor about that. So yeah, but yeah, this is just very random. I don't have yeah. Yeah, it's possible to change the different type of material. So for example, you could put it on the textile, on the different things, yeah. Oh yeah, the generator, the triple electric neural generator is kind of a new material. It generates the signal by itself. So it doesn't have any power. It just generates the power itself. So yeah, it's just like the piezo or like something else. But yeah, it could also be used for energy harvesting. Yeah, that's a very cool question. So yeah, my vision is to make every material intuitive and makeable. But for like plastic, it's sort of like an injection approach. So for injection approach, maybe we need to think about how to really make it makeable, right? Because it's really hard. Think about a single fragment, how to make it like really makeable and capable to bring the new interactivity into the object like using the 3D printer to print it. Yeah. So it's I don't have the right answer for that, but yeah. 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 So actually, when you have a quite static movement, it still causes a vibration, but it's small. And this sensor could still sense such vibrations. Yeah.
Because we are almost running out of time, we will save this question for the coffee breaks and the lunch breaks. Let's thank our speaker again. Our last speaker is Zhe-Yu Yan from University of Maryland. He will be presenting on behalf of his collaboration with George Mason University as well. Fabricate prototyping high-resolution flexible and kirigami circuits with a fiber laser engraver.
All right, thanks for the introduction. So hi everyone, I'm Zoe from University of Maryland, and today I'm presenting you Fabricate. I think the projection messed up my. Oh, let me just. All right, so in Fabricate we present a set of techniques that allow us to fabricate high-resolution, flexible and kirigami circuits with a fiber laser engraver. So this work is in collaboration with my co-first author, Anup Sathya, and Sarah Yusuf, Professor Zhiming Lian, and my advisor, Huai Shupeng. All right. So nowadays, we design and prototype really complex and form factors with a low-cost 3D printer in hours, in a really short time. But then we're missing a 3D printing equivalent for high-resolution PCBs, especially for the applications that requires the higher resolution and the flexibility or like complex form, such as wearables or IoT devices. And previous research has tried to tackle this problem using either inkjet printer or CO2 lasers to manufacture conductors, but oftentimes these are limited in resolution and sometimes conductivity as well. There are also high-end machines such as a dual source laser that are involved in the same goal, but then these are usually not accessible in our lab spaces or maker spaces. So in Fabricate, we aim to fabricate high-resolution, flexible, and kirigami PCBs with an affordable machine, which is a fiber laser engraver. These are the same machines that in the industries used to, for example, engrave your AirPod cases, but then these are now widely available in a maker setting in different platforms ranging from 2 to 5K. And we repurpose this machine to fabricate PCB. And here's a glance of what we can make out of these machines and our process. So in the rest of the presentation, I'm going to be break down this Fabricate and then let you know what we did and how we do it. Starting with a brief introduction of fiber laser, and then followed by the minimal fabrication process towards a working PCB prototype. And on top of that, I'll present several other techniques on top of that to gain more versatility in the PCB outcome, instead of just making a square-shaped stiff PCB. And then I'll give you a set of example circuits that we made with Fabricate to showcase how we can utilize in different applications. So without further ado, let's dive into what a fiber laser is. So fiber laser utilizes a diode laser source, different from the CO2 laser source. And then the laser beam is transferred from the source towards the lenses using optical fiber, which is why it's named fiber laser. And then the beam is going to be reflected towards the working area with a pair of galvanometers for high-speed scanning. So more intuitively, from the material perspective, the CO2 laser has longer wavelength than fiber laser. It can work on organic materials pretty good, like wood or plastic, but not on metal. But fiber laser with the shorter wavelengths works really good on metal, which makes it a perfect tool for fabricating PCBs. Right, so now we know what fiber laser is, and let me show you our fabrication process towards a working PCB prototype. So to achieve the functionality of a circuit, we choose copper sheets as a material for the conductor layers because it's good conductivity and wide availability. And we use Kapton tape as our dielectric insulation layer material because it has really good heat and electric insulation property, which feeds both the laser cutting process, also the goal of making PCB. So to make the cutting substrate, we basically laminate these two types of material together and feed the sandwich through a press roller, in this case a pulsar roller, and then optionally you can punch alignment holes to fit your laser jig or laser pad. So now we have this material substrate. Now we have to think about how to make traces, right? So there are two parts of the two key things we have to pay attention when we're making traces. First is that there are isolation areas between traces to prevent shorting, so these areas has to be there without the conductors at those areas. And then in our goal, we also have to be able to remove the copper at those areas without harming the Kapton material underneath, so that the outcome PCB is still one piece after cutting. Right. So to achieve that, we propose to vector cutting the outline of the isolation areas so that physically the copper at those isolation areas are detached with the traces. And then you can peel off the isolation area copper really easily with a tweezer. To achieve this good calibration of laser power versus like I'm only engraving copper but not harming the Kapton, we present a set of parameters for different copper thicknesses using basically varying the laser parameter combination, including speed, power percentage, pass number, and some cooling time combination, right? This is a glance of some of the parameters, and you can refer to our bigger table in the paper. Yeah, so to give you guys a sense of how this process looks like and how fast this can happen, I brought my laser. So let's turn off the ventilation and the laser. Yeah. So I'm gonna pull my software on to the screen and then okay. So firstly, I'm going to try to engrave the traces, basically the outline of the insulations. And this is a 0.05 thickness copper, so using the parameter corresponding to that, which is going to take, hopefully the calibration is okay. Oh, that was the lighting. Well, basically, let me just is there I'll still stop tuning that. But anyway, we have another piece of live demo at the second part of the presenting. But then let's just move on with a video that I took earlier. I don't know why this. So this is a video that I took when I was cutting one of our example circuits, and then this is kind of like the process of how it outlines the isolation areas, and then also like we can also cut through holes and cut the outline of the PCB with a higher energy density setting, aside from the isolation scanning, and then you can take it off the PCB. So obviously with the hole and the dimension cutting, we will use we'll basically penetrate both materials, both the copper and kapton. Right? And so basically after that, peeling the isolation area copper off and then solder all the components on, then we'll have a working functional PCB prototype. These are the two example circuits that we made. There are actually Arduino Nano equivalents. There's a double layer setting on the left-hand side and a single layer on the right-hand side. So we want to highlight a couple things about this process. Firstly, it happens really fast. So both samples are made with a machine time less than 5 minutes. And so it's ideal for fast prototyping. And on top of that, we have like really high resolution profile that we can cut with this process. Numbers are shown here. Like minimum trace width we report is 8 mil, and minimum clearance is 4 mil. So yeah, so this is basically on par with a lot of small batch manufacturers already. So you don't have to outsource for your PCB and you can make it in-house. And this number is achieved almost 100% of the time, so it's really reliable. Yeah. So now we can make high resolution PCBs. We have a 3D printing equivalent using our process, but we can do more. So on top of that, we can actually tune the flexibility of the outcome PCB by tuning like the material combination. We can also use the laser to help soldering components on it. And then we can also make Kirigami circuits in 3D form so that we can combine the form factor and the electronic functionality in one package. So you can refer to the details in the paper, but today I'm going to highlight the laser soldering and the Kirigami circuits. All right, so the key in soldering is really to generate enough heat to melt the solder paste at the solder pad so that you make connections, right? And in this case, we present two ways of doing it. The first way is to directly engrave on the extended pins of the components. For example, this small IC. A diagram in the diagram would be shown on the blue areas. And then if the components doesn't really have an extended pin, then we can design an extended solder pad so the laser can work on those areas to generate heat and works equivalently well. And then this is actually the opening scene that I've shown. If you may have wondered what this is that I'm trying to solder the battery onto the circuit to complete the circuit so that the LED shines. Yeah, so with this process, we can solder really small components onto the circuit, which is otherwise really hard manually, including small ICs and even a 402 package resistor. Yeah, so, and then aside from soldering, we can also do, as I said, 3D circuits with Kirigami process. So basically, we want to combine the form factor and the electronic functionality in one package. Right, and then we employ the method called laser forming in this process. So in a comprehensive way, laser forming means to bend the material with the laser. And for metal sheets, the principle is like with the extensive heat difference across the top and bottom like surface, the microstructure will have a permanent deformation so that the material will bend towards the hotter side when you're engraving. Right, so yeah, so this is an example of what we can achieve. And then to computationally control this bending angle, we experimented with different thicknesses of coppers, and then basically the number of passes with the same parameter engraved on the hinge location will cause different bending angles. So basically more times that you engrave, the higher the bending angle is. So let's give the laser a second chance so obviously that was the video, but then let's give it a second chance, see if we can make the bending happen here. But if it doesn't, we'll have a live demo at the demo session this evening, so you can see this effect again. Let's just, all right. So this is kind of like, I'm trying to engrave that shiny location on the copper to make a bending hinge on that. And then, so basically that was a really light engrave, and if I increase the power and increase the pass number, it'll bend, so I'm gonna do that right now. And this is really sensitive towards basically how far your laser focus is from your material. Obviously, we went through a lot of traveling with the laser, so yeah, that's basically what is key to this process. And you can see a light mark already, and then if we do more of the engraving, it would be able to start bending up. So you can see this bending process actually happens like in kind of a real-time-ish in time frame. So we can also make 3D circuits relatively fast. I'm going to stop it here, and then we'll have more organic form factors bending in our live demo, so you can drop by to see more. Yeah, so basically we present, other than this sharp hinges, we can also offset this hinge location to different places or different like offset spaces so that we can create either organic curves or also fillet hinges, depending on the application. So we also prototype a small software interface for the designers to create their own Kirigami circuits. So basically all we need from them is the outline of the circuits and the hinge location and specifications, and we'll have a live simulation of the top left corner for the results, for the anticipated results. And so once this file is being parsed, we can start cutting. Right, so once the cutting is done, you can put in the power source and you have a circuit with the 3D form factor in one package. So along with this screen, we present you several other application examples, including a miniature earring that we can embed the circuit together into the form factor. We also custom a end stop switch for Ender 3 Pro, so that we can, so that should show you that we can make mechanical functionalities built in as well. Happy butterfly coil, and then also a squiggly cable for Raspberry camera is only possible because our high resolution flexibility that we can afford in our process. And these settings are really good in terms of making wearables or on-close applications where you need the reliability at the same time of like high resolution, right? So I would like to conclude FiberKit now, and then I would believe that FiberKit is kind of like a sound first step for fabricating high resolution PCBs in-house, and then there are a lot more that can come in the future, right? And then before I take questions, we have another work from our lab featuring a web layout design tool for blind people. The talk is going to be tomorrow in the accessibility session, so feel free to drop by. And both projects will have the demo in the evening. So with that, I'd like to take questions about FiberKit. Thanks.
Okay, I have one question about the
Yes.
materials. How big can you achieve by this 3D machine? I mean,
Yes, that's a good question. So with this current setup, obviously everything is going to be limited by the laser lens and the laser working area. Well, it's kind of like a matter of effort and the availability, right? Like, so this current lens is on the laser is 10 by 10 centimeter, but 10 by 10 centimeter, but we also have another lens available for 30 by 30. So you can think about it's like a similar size of Ender 3 Pro building bed size. So you can make comparably large circuits as well. Yeah.
Let's thank all our speakers. Sorry, we are running out of time. The author will be here hanging around. Please come and stay for more conversation.
Yes.
So the session is done for today, morning session. We are gonna come back at 2:30 for the afternoon session. And there are the QR codes that you can scan and then vote for the best talk. If you liked any of the talk today, please vote. And we will meet again 2:30.
Yeah. Okay.
Test, test, test. Test, test, test. It's very silent, no? It's not really loud, right?
Yeah, that's okay.
That's okay? All right.
Yeah, but I hear it.
So, all right. We have, it's time to start the session. So, welcome to the soft and deformable material session. I will be your session chair this afternoon. My name is Michael Wesley, Aarhus University, and we have like 6 absolutely amazing projects that our amazing presenters will show you today. And it's even like a little bit special. So we have one Tokai paper where the authors decided to present their work here. And we also have one project that got awarded the best paper award at UIST. All right, then without further ado, like the first project that we have is called Anisma, a prototyping toolkit to explore haptic skin deformation applications using shape memory alloys. And the authors are Moritz Alexander Messerschmidt, Zafid Muthukumarana, Nur Al-Huda Hamdan, Adrian Wagner, Haimo Zeng, Jan Borchers, and Suranga Chandima Nanayakara. My pronunciation was most likely extremely off, but please forgive me. All right, then let's welcome Moritz.
All right. Hello? Test, test. Okay, good. All right. Yeah, as Michael said, my name is Moritz. I'm a PhD candidate at the Augmented Human Lab, and in general, my research interest is in looking into new ways in how we can integrate haptics and the new evolving environments of extended reality. And I especially like to do that by looking at smart materials. And today, I'll present my work on Anisma, a toolkit to explore haptic skin deformation applications, focusing on a smart material called shape memory alloys. And I wouldn't have, this work wouldn't have been possible without my fantastic colleagues, SIGCHI Muthukumarana, Nur Hamdan, Adrian Wagner, Haimo Zeng, Jan Borchers, and my supervisor, Suranga Nanayakara. So, getting started. Okay, this is the last slide. Sorry for that. So you get a quick preview. So if we're looking at the current trends of interaction technology, we see that all the big companies are working towards a vision where we'll work in environments that are going to be more immersive, with three-dimensional environments, asking for more natural and intuitive interactions. And these require, maybe I can use this. These require, is this on? No, right? I'll just use this one. Okay. This require a different type of, different requirements for technologies. And as you look at the technologies, you can already derive 2 requirements for these technologies by looking at this trend. And it is a high expressibility and a high wearability. And if you look at haptic feedback at the moment, all right, is it working? Okay, I see. You mainly see vibration motors still in the consumer products. And while vibration motors are awesome, they are compact and affordable, they're not as expressive and mainly suited for providing abstract vibrotactile cues. So that drove previous work in looking into how to provide more expressive feedback. And they came up with a lot of different approaches using conventional actuators. You see electronic motors, pneumatic pumps, and solenoids, hydraulic systems. But these systems implement a lot of mechanical elements, which result in systems that are quite heavy, noisy, bulky, and rigid. However, if we look in some more recent approaches, researchers have increasingly looked into shape memory alloys and proposed them as a compelling material that might be interesting to provide more wearable and more expressive haptic feedback on the skin, complementary to vibration. And they showed this in a variety of implementations to provide more expressive and natural feeling sensations. And the question is, why are shape memory alloys so attractive? Well, they have a couple of promising characteristics, like they can act as an artificial muscle, they have a smooth and powerful contraction, a high force to weight ratio, and they have lightweight, flexible, and thin properties. So on the right side, you see a demo of like a short contraction using a spring. And so we looked at previous work, and also based on our first testing with shape memory alloys, we got a sense that there are a couple of prototyping challenges out there, and that drove us to look a little bit more into what these prototyping challenges might actually be and how serious they are. So we did this in two ways. First of all, we looked into conducting a focus group with 5 HCI researchers that haven't had previous experience with working with shape memory alloys, but were interested in applying them for haptic applications. And we looked into how you work with them and what challenges you might face by approaching to create these and implement them for these applications. And the second thing we did was we looked at people who already have experience working with shape memory alloys, and we interviewed them about the challenges they had and what things they could foresee that might help them. So based on these two, we derived 5 main challenges for prototyping with shape memory alloys. First, heat protection and encapsulation, because they heat up. A robust attachment, because the contraction can be quite strong and dismantle it from the device embedded or even from the skin. A steady and accurate control, because SMAs have a nonlinear actuation behavior, which is not as intuitive, and they're especially harder to control over a longer time. And then there we have operational limits and other parameter determinations, which are not as intuitive and obvious. And from our focus group, we saw that especially novice users struggle with using just the data sheet or other documents to simply try to derive them easily. And from the interviews we saw, it ended always in a lot of try and error. And finally, the implementation effort, which is just an immense time effort in prototyping with them. You have to apply a lot of skills in designing and coming up with the design and fabricating at the end. So this is what drove us to develop Anisma and tackle these challenges and provide a system that helps HCI researchers to explore haptic applications using them. And as you can see, Anisma is based on a quite simple concept. The concept is you're working with SMA modules, and each module consists of an SMA spring that connects 2 SMA nodes. And the nodes can either be attached to the skin to direct the skin, or pull an object. And you can combine these SMA modules in various ways and create interesting, quite complex topologies and actuate them, program them. So here you see like an example of a slider device. And on the left side, you see the software implementation, and on the right side, the actual fabricated device. So Anisma supports you all the way from the initial design to the final product, and I will demonstrate a brief workflow here. So you can see that the user starts in the software environment designing the actuator layout, connects the SMA modules, and can already program and preview the actuation behavior, and already derives some indications on whether the user is running into issue, can quickly iterate on the design and refine it. And when the user is satisfied, can quickly export it on SkinF and print it on SkinF adhesive. The node mounts and the layout will be printed on that. And as you can see now, the user can use some of our hardware components. First applies heat insulation tape, then sticks customized nodes on the corresponding node mounts, and then simply connects them with the SMA springs. And afterwards, you can quickly take the patch and apply it on the skin. Then you can connect it to the customized driver board and use that to simply replay the previous programmed actuation behavior. And you can do that and view the preview on the left side and the actual behavior on the skin. But the most important thing is that you can now quickly verify the actual haptic perception. While you can go back and redo the whole process, you can also go back, if you have a topology like that, and reprogram the device and test multiple actuation behaviors directly on the skin. So what we did was we evaluated our system in 3 ways. And we will today just focus on experiment 3 because of time reasons. But in the first experiment, we did a technical evaluation we basically looked at our empirical model we developed describing the actuation characteristic of the SMA, and looked at that it's working consistently and allows working over longer time to operate the SMAs safely. And in the second experiment, we looked at the perceptibility of essential skin deformation devices supported by our system and verified that. And in the third experiment, we look a little bit further now. We looked at, is the toolkit actually useful by looking at the usability and the supported creativity. And we did this by inviting 12 HCI researchers, 4 from our focus group in the beginning and 8 new users. And we had 3 sessions. In the first session, we gave an introduction on how the SMAs work and demoed a very basic device process and the workflow. In the second task, we gave the users the task to develop a slider device, which is simple, and we gave them subtasks that led them through the system, so they got in touch with the different components of the system. And the final task, we designed open and asked them to design 2 skin deformation devices to convey an emoticon, which could be an action or a motion using shape memory laws. So here you see a couple of the designs the users came up with. On the top you see always the software view, and on the bottom the physical implementation. And as you can see, the users came up already with a variety of applications. While they were using the basic elements, they came up with quite diverse designs. And if you see on the bottom of the software part, you see they already were working with quite confidently with longer actuation sequences, which is something we didn't see that much in previous work that far. And yeah, showed that we could support them for long actuations, which was quite interesting. In general, they took 60 minutes, around 60 minutes to fabricate 2 on-skin haptic devices. And after that, we asked them to rate 2 metrics. The first metric aimed for the usability. Probably you all know the system usability scale. It asks you for a couple of questions from 1 to 5 whether you agree if you agree or disagree. So on the left side, we plotted the positive statements where we'd expect high rating for a positive result, and analogically negative result, like low ratings on the right side would be also good. And as you can see, the system was rated quite positive. Help needed a lot of learn. We come in a minute. But overall, the result was good. We also investigated the creativity support index. Here the users first prioritize different criteria and then evaluate them subjectively. On the right side, from 1 to 10, 10 is the highest rating. And what we here were happy to see was that the users found exploration and expressiveness most important for this tool, and they also rated it high. We got some qualitative feedback from the users we collected through interviews at the end. A lot of users were quite enthusiastic about the tool. On the bottom left, you see users were not happy with all UI elements, and they were partially a little bit complex, but overall the tool provided a sandbox so they could quickly learn how the functionality was by just setting parameters and trying out what happens. So coming to the last point, maybe quickly, limitations. At the moment, the actuation model is an empirical model and doesn't base on a feedback loop. That means it guarantees that you can safely operate the SMAs, but it restricts how you can actuate the SMA in general. So working on that and improving that would help a lot. Feedback control loop would give you much more control about the actuation behavior, of course. And a cooling system could in future increase the actuation frequency. So with that, I will finish up, and I'm happy to receive questions and try to answer them. Thank you.
So if you have any questions, please come here, queue up, and communicate with the owner. Do we have any
experiences with your prototyping tool. So I can imagine it's pretty easy to design haptic feedback when it comes to viral tackle, because I think with current like viral vibration actuator getting high resolution, you just like grab an audio file of any impulse feedback into just a vibrator. What would be like, for example, imagine that you're like a VR designer, want to design any haptic feedback occurs in the VR. What would be what's your take on your tool as a VR haptic prototyping toolkit?
I think it's a good question. I think the SMAs are, with the current limitations, not the answer to all. Like, you cannot create arbitrary haptic feedback, but especially for slow actuations to create natural feeling sensations, I think they're very well suited. And maybe what you might be thinking of, I think this could be one side on like covering one part of providing haptic feedback in virtual reality scenarios. But I think using a complementary to vibration would create even more expressiveness. So in my view, SMAs are especially suited for providing these skin deformations. That means, yeah, stretching, pulling.
I see.
For, yeah.
Thanks so much.
Thank you.
All right, then let's thank our speaker once more.
All right, thank you.
So the next presentation that we will have today will be a mode representation. COVID-19 restrictions, so authors unfortunately couldn't make it here. So the project that we will see right now is X-Bridges, designing tunable bridges to enrich 3D printed objects deformation and stiffness, by Lingyun Shun, Jiaiji Li, Junse Ji, Deyang Pan, Ming Li, Wang Qi Zhu, Yitao Fan, Yue Yang, Yitao, and Wan Yun Wang. So, and we will start with a video presentation right now, and the author will also be here to answer questions over Zoom.
So we do have a bit of an issue with the HDMI connection, so I think we might need to play the audio through the laptop and hope that the microphone picks it up. So apologies for that.
Welcome to the virtual presentation of X-Bridges, designing tunable bridges to enrich 3D printed objects, deformation and stiffness. I'm Jiaiji Li, and I will be presenting our team from International Design Institute of Zhejiang University. Bridges are unique structures in fused deposition modeling, FDM printing, that make rigid prints flexible but not fully explored. X-Bridges is a design tool to allow novice users to design tunable bridges that can enrich 3D prints with multiple behaviors of tunable flexibilities. Compared to existing method, we adapt the advantages of metal material, fabric manufacture, and parametric remodeling tool for quick prototyping without post-process. Our parametric design tool creates tunable stiffness of connections, including stable, elastic, and loose, which allow users to on-demand modify with the final artifacts. We should start from FDM printing to explain the mechanism of X-Bridges. In FDM printing, the certain toughness of filaments enables it to resist gravity at a short distance, which is so-called bridges. We take advantages of extra compliance of it to perform both flexible and rigid with one material. All further research design it as connections for solid sheets, origami, blocks, torsions, and stretchable structures. I will take the wheel again as an example to introduce our workflow. Firstly, virtual models is imported and divided into multiple parts. The gaps in between enable deformations. Users can adjust reform position, deformation angle, and the gaps amount to get their ideal result. We conducted a series of tests in order to determine the optimal parameter and their interplay for X-Bridges. Among all the parameters, bridge densities, extrusion flow rate, and print speed have dominant effect for physical properties of bridges. We also use some quantitative experiment to distinguish plastic deformation from elastic deformation, together with extrusion control algorithm to calculate the actual filaments for relative extrude mode for further G-code generation. The experiment results were integrated with X-Bridge design tool. With options of stiffness, the G-code would be generated accordingly with different settings. Here are three results. The first one is stable, with minimized bridge's length and the largest extrusion. The reformed tail keeps its shape after being manipulated. With medium extrusion, longer bridges would be elastic in a certain range, which would keep objects bouncing back just like spring. With the minimum extrusion parameter of 70% and a minimum printing speed, thin and long bridges are no longer stiff enough to resist the gravity. Besides the tunable stiffness, we develop deformation structures including bend, stretch, compress, and twist. Though some of them seem similar to existing structures, they are consisted of flexible bridges and rigid parts, so all deformation only occur on bridges, which could be well controlled with printing parameters I've mentioned before. We also made some samples to explore the design spaces for developable surfaces like origami. Here we leverage tessellations of mural folding and curved folding. And also we leverage a vase with non-developable surfaces and stable bridges, so it could stay the shape after manually deformed. By replacing part of a metal material cube with different density of bridges, it performed pretty different with same pressing force of 10 Newton. Though these tiny bridges seems vulnerable, our fatigue limit test shows that it could be deformed more than 7,000 times in 4 hours. Then I will show some applications to indicate what we can really do with X-bridges. X-bridges allows us to make modification and fabricate everyday products in different scales. For instance, a hanger. We're replacing the shoulder and the pants part with stable stretching structure so it could fit both adults and children's clothes. With loose bridges transferring motions and rigid bridges connecting bars as crosses, we also present a fully functional crocodile toy that can extend and retract by trigger. In next example, we showcase 2 bunny ears with different parameters. The first stable pair is only deformable by extra manual forces, while the second loose one would swing freely with various motion of jumping, dancing, or even simply walking. Rather than regular even extrusion, we modified the G-code file to increase extrusion flow linearly from 80% to 160%, which gives the button a resistant gradient on the layer for every segment. In conclusion, shape changing, physical property changing, and model reforming features enable our design tool to generate multi-form and multi-use applications. We look forward to applying our method to future sustainable fabrication. Thank you for watching. Welcome to the virtual presentation of X-bridges. Designing. Hey.
So, hello. Can you guys hear him?
Hey.
Yeah, looks good, no? So, alrighty. So we have already people keying up for the question. We will see if you can understand the question. Otherwise I will repeat it for you. All right? So.
Yes, I can hear you.
And can you please say like your name because he cannot see you?
Yeah. Okay. Hi everyone. I'm Zhaji Li. It's a great shame that I couldn't come to the meeting to join you guys, but thanks for watching the videos, and I'm ready for any questions you have. Yes, thank you for turning me around.
Yeah, so I have a question about the materials. I'm not clear to see that the tails material and the bodies, the material is the same material or different materials. Would you want to introduce more about the materials? I mean, would you want to introduce more about material? I saw the tail materials and the body materials, they use the difference or the same?
Thank you, thank you. I mean, yes, I know you are asking about the materials. I mean, not do the most like performance of videos shows before, but we use some specific material called Polymax PLA. It's actually a mixture of a certain proportion of TPU with inside the PLA, so it would make it perform better and more tough for deforming after printing. Yeah, thank you for that.
Okay, thank you.
Sorry, I can't hear the questions very clearly.
Yeah, okay, then I will better repeat them. So at the moment we have no one like queuing up at the moment, but I was also like wondering in a very similar question. So like, you know, when you like 3D print something, you can use like PLA, so like a very rigid material, but also like soft materials. And I was wondering if you maybe think about like having a more structured approach to this for like filaments that can be very soft, like in a continuous spectrum, to very hard materials, and integrate this into your model. Do you think this would be possible and you would have benefits from this for X-Bridges?
You mean like printing the filaments very long and soft, just like a fabric, or like just like a longer version of the loose state of the shown in videos?
I like this question actually as well. So yeah, what would happen if you make it longer? Yeah, what do you think?
Make it much longer, or like suitable for fabric, like to fit more human beings. Yes, we're considering about that, but we try to like focus on the very micro bridges, and it's like enlarged by the solid ones, by the rigid parts. We like to see the two properties printed with one material in this paper, but your suggestion is very like inspiring, so we will do it in next work or in future. Yeah.
Nice, I like to hear that. All right, then let's thank our speaker once again.
Physical presenter again. So the project that we will see next is called Prototyping Soft Devices with Interactive Bioplastics, with the authors Marion Kölle, Madalina Luciana Nicolai, Aditya Shekhar-Nitala, Marc Tessier, and Jürgen Steimle. And today we have here Madalina. So let's welcome her. Madalina, take it away.
Thank you very much. Can you hear me? It's okay? Okay. So my name is Madalina Nicolai, and today I'll be presenting prototyping soft devices with interactive bioplastics. As Michael said, this work was done in collaboration with Marion Kölle, Aditya Nitala, Marc Tessier, and Jürgen Steimle at ACI Lab of Saarland University and Da Vinci Innovation Center. Well, bioplastics are bio-based and biodegradable materials compliant with most of the digital fabrication techniques. And biopolymers, their main component, are abundant renewable resources with unique inherent properties, sometimes synthesized by the cells of living organisms. Therefore, their versatility and potential to uphold sustainable processes makes them very attractive as prototyping materials. And a wealth of bioplastic recipes shaped as books, books, community archives, or physical archives make these materials extremely accessible, actually. However, if we have a look at the prior work, most artifacts rely on passive objects or are made functional by embedding rigid electronics components into them. So, for example, numerous projects from design community showcase bioplastics used for product design, and although they give a glance on how these materials can be combined with digital fabrication techniques, they are limited to passive artifacts. Also, several biomaterials such as mycelium, bacterial cellulose, and agar-agar have already been explored by HCI community for user interaction. They are used as functional sheet material or as substrate or encasing material for rigid electronics such as LEDs or wearable circuit boards. And they open up new design spaces, but the use of the biomaterial itself as main electrical interaction platform is yet missing. And so therefore, our main question was how can we enable DIY creation of functional and sustainable soft interactive devices from bioplastics? Our work presents an accessible end-to-end approach for the DIY fabrication of 3 types of conductive bioplastics: sheets, paste, and foams. And we combine this with additive and subtractive fabrication techniques to build a variety of sensors such as bending sensors, electrodes, or pressure sensors. Finally, we provide the characterization of the functional properties of our materials and devices as relevant to the DIY fabrication. Through these contributions, we aim to create a design space where sustainability, functionality, and DIY fabrication can coexist and take advantage of each other. And how do we achieve this? Well, we focus on sustainable alternatives that originate from nature, allow interaction, and at the end of life can be returned to nature. So first, our base materials originate from nature. The main materials we use are carbon particles, natural fats such as beeswax, and biopolymers such as gelatin and sodium alginate. Easy to functionalize, we use water and simple household materials actually to synthesize the main conductive materials of our work. For example, here you have the synthesis process of the conductive alginate sheets that, so it's an extract from algae, an food additive that you usually eat in your daily life actually, that after mixing with carbon and being dried, we obtain quite conductive biodegradable sheets. And once dried, we can use plotter cutter to actually cut, to shape them and create different designs. And using this plotter cutter, for example, the smallest traces we were able to create were 1.5 to 2 millimeters wide. Therefore, the versatility of these materials makes interaction possible and really accessible. For example, first we create conductive sheets for thin on-skin applications such as stretching sensors. Our sheets are synthesized from alginate, glycerin, carbon black, and calcium lactate. And each one of these ingredients actually provides new properties to the conductive sheets. For example, adding more glycerin increases the softness and elasticity of our material. Here, the red curve being the lower ratio of glycerin and blue being the higher. Adding carbon makes the sheet conductive, but weakens the polymer matrix, making it more brittle. The difference can be seen in the green lines, the pointy line being the conductive one, the other one being the non-conductive version. So taking in consideration the constraints of the applications we wanted to develop, and the composition of the sheet was actually tuned to find the balance between the mechanical and the electrical properties. Our main conductive compositions contain 2.3% of carbon black, and once dried, its thickness measures under 0.2 millimeters thickness. the elongation averages 2.25%, and the resistance is around 32 ohm square. All those tests allowed us to build functional devices. Here you have the stretching sensor made entirely out of alginate bioplastics fixed without any additional adhesive. Working also with food-grade carbon particles, such as activated charcoal, we can create food-grade sensors, for example, capacitive macaron that can talk to you when you want to eat them. And next, another important material in ACI are pastes. So pastes are a crucial material to create connections between different components and easily design conductive traces that allow us to create sustainable boards, for example. Our conductive pastes are synthesized from off-the-shelf adhesive based on starch and carbon black. So our resistance tests, conductivity tests, actually show that the performance of our main paste, which is Cleobio carbon black 10%, the performance is on par with commercially available conductive paints or paste. And depending on the substrate the paste is applied onto, it also remains flexible actually once dried, which is not always the case for commercially available paste. So pastes are available too, as they allow us techniques such as stencil painting. Here you have the circuit wax board with an Atitiny and an LED powered by a battery coin. But of course, paste can also be used to do freehand painted design for more design freedom, for example. And let's not forget, as conductive soft adhesive, they also connect off-the-shelf rigid electronic components and organic, soft, flexible, very unconventional materials, such as our alginate paste, alginate sheet. So lastly, we create foams for conductive foams for volumic interfaces, such as pressure sensors. The foams are synthesized from gelatin, glycerin, carbon black, and bio-based dish soap. And our electromechanical tests show that the resistive response of conductive foam is proportional to the load applied the day we made it and also after 4 days, which means that we can create, we can build real-time responsive sensors out of biodegradable materials. So almost every application presents different fabrication technique and takes advantage of the inherent properties of the material. Sheets, foams, and pastes are 3 primitives that can actually be combined to create a wealth of more complex devices, such as, for example, EMG electrodes that combine the paste conductivity, the gelatin screen printing stability, and the alginate adhesiveness. So for example, with this example, we demonstrate how these materials combined with digital fabrication techniques can substitute conventional prototyping materials or be combined with off-the-shelf electronics to create a wealth of new interactive devices. Finally, as I said, we focus on materials that at the end of life can be returned to nature. And we can do this depending on their composition. They can be disassembled and either reused, remelt, or composted. And for example, for our electrodes, after disassembling them and a little bit of manual cleaning, we can actually reuse the connectors, compost the paste, and remelt the gelatin to create new design sheets, for example. Yet, using organic materials is, in a DIY setup especially, is not without limitations on which we reflect and discuss a lot in detail in the last part of our work. So among these limitations, the importance of environmental conditions is the most notable one. Naturally, the performance and durability do not match the industry standards, simply because being organic, they are made to be ephemeral. So their lifespan is actually very short. Another important factor is time. These processes require an incredible, but not impossible, time and production management before being able to make like full devices. Despite all this, however, the number of possibilities remains very large, and we believe that by opening up a space for prototyping electronics with bioplastics, this work can act as a valuable starting point for sustainable prototyping in the future. So thank you very much, and all our prototypes will be available during the demo sessions if you want to try to touch them and so on. Thank you very much.
Hi, my name is Jasper from the University of Washington. Super cool work. We can't wait to see, like, actually get my hands on these demos. I was curious if you thought about, like, these are kind of the input and output elements of some prototype, but I'm curious also about like the structural elements and enclosures. Is there prior work on having bioplastics as like enclosures or other, I guess, more structural elements, and how would that interface with these?
So we focused mainly in this work on the sensing. There's a little bit work on the output, but yeah, as I said, the lifespan of these materials is quite short. So compared to the biomaterials used for encasing, the conditions for storing or their conditions to work are actually very different. They cannot be stored the same way. So their interfacing, like if we try to interface them, they may affect each other in a negative way. So the materials need to be very careful choosing which one like matches with which one.
Thank you.
Very cool talk, Magdalena. I'm Pedro from the University of Chicago. I'm just really inspired by the ecological part of it, right? The fact that you can return these things to nature. And you mentioned a little bit that cutting them small was really difficult. Could this be explored? I'm imagining like you have infinite money and infinite resources. You know, could you make a small transistor out of this? You know, have the tiny be built from a bioplastic or something like that? Or are we really far from that future? And I know I'm asking you to speculate. Go for it.
Honestly, so using carbon black in a DIY setup especially, and trying to make work accessible to other people, yes, the traces that we can cut are actually limited. We try to use like normal material that you can even have at home and like this. But of course, I think that with like a huge lab, and maybe the guys in material science actually are able to use this kind of materials. I know that there is a bunch of work in material science, very interesting, that uses bio-based materials, but I think in our work we don't focus on the same thing. They focus on their like properties, functionality of it. We try to focus more on the accessibility part of using these materials.
Getting people to use it. I think you did a great job with that. Thank you.
Thank you.
So, all right, let's thank our speaker once again. And in addition, I have like a very special honor today. This paper received a Best Paper Award from the ACM WIST conference, and we have like here.
Wait. If you want to take a nice picture, I need to.
It just makes it better. So, and it's my great pleasure to give you the Best Paper Award at ACM WIST. Congratulations.
This work couldn't have been accomplished without the help of all the people mentioned in there. It's a year actually of work in there, so it's an award for everyone.
All right, thank you. So then let's move on to the next project. Next project is also super awesome and interesting, and it's called a sketch-based design of foundation paper peaceable quilts. And the authors are Mackenzie Leake, my ex-lab mate, Gilbert Bernstein and Manish Agrawala, and today presenting will be Mackenzie. So, and while she is setting it up, yeah, we can already welcome her. So let's welcome Mackenzie.
Thank you. So hi, I'm Mackenzie. I'm a postdoc at MIT CSAIL, and I'm very excited to present this work with Gilbert Bernstein and Manish Agrawala on sketch-based design of foundation paper pieceable quilts. So foundation paper piecing is a popular quilt-making technique that allows for many different types of geometric and representational designs. So to construct a paper pieceable quilt, we start with a design like this one, and then we cut the fabric for each face in the design, sew the fabric to the paper in the order specified by the design, and then remove the paper to obtain the sewn result. So this process of sewing to paper improves precision and adds stability, so lots of new quilters like to use this process. And it's actually a very popular technique overall that most quilters have used at some point or another. But the process of sewing a design to a piece of paper constrains the set of designs that are possible and the order in which you can attach the fabrics. So in previous work, we came up with a method of determining if a design, like this one shown here, is paper pieceable. And to do this, we frame this as a disassembly problem. So since we're working in reverse, we'll start at the ending state with colorful fabrics attached to each face. So for explanation, we'll label the faces, and we'll say that the primary foundation paper piecing, or FPP constraint, is that it must be possible to remove one face at a time by cutting along a single seam line. So here, the only face that we can remove that way is face A. For example, if we tried to cut off face C along its top edge, it would still remain attached to the paper along the left side. And trying to remove B or D at this point wouldn't allow us to remove a single face at a time. So we go ahead and we remove face A. And now we see that face B is the only one we can remove, since C and D are still stuck to the paper as before and can't be removed with a single cut. So let's remove B. And now we can remove either C or D along the seam between them. So let's remove C, and finally D. And we've now completely disassembled our design, so we can simply reverse the removal order to get our sewing order back, starting with D, C, B, and finally A. And this is the full process. And this constraint here applies to complete input designs where all of the edges extend to the boundaries or other edges. So we came up with an algorithm that efficiently identifies the removable faces by representing the design as a hypergraph in which each face is a node and each seam between the faces is a hyperedge. And then we perform the equivalent of a topological sort on the hypergraph to determine a sewing order. But to do this analysis, however, we need to know the topology of the faces. But we learned that in practice, quilters tend to sketch designs iteratively by focusing on edges instead. So in order to better support how quilters typically tend to work, we developed a new representation that focuses on edges rather than faces. And so again, here, we'll think about this as a disassembly process and start with the end state with all of our fabrics sewn to the paper. So in this representation, we can express the paper piecing disassembly constraint as saying an edge is cuttable if one side of it is free of other edges. So for example, here E1 is cuttable because it has no edges above it. But E2 would not be cuttable because it has E1 on both sides, and likewise E3 wouldn't be cuttable because it has E2 on both sides. So we therefore start by cutting E1. And this time, instead of a hypergraph, we'll represent the sidedness of the edges using a BSP tree. And so we make E1 the root node of our BSP tree. And now we'll check again, and we see that E2 is the only cuttable edge now, and E3 is still not cuttable because E2 is on both sides. So we cut off E2 and add it to our BSP tree. So there are more details about the construction of this BSP tree in our paper, but the key part is that the algorithm picks an arbitrary positive and negative direction to represent the sides of each edge. And you'll see as we build up this tree that one of the sides will remain empty for each node because of this disassembly constraint. So then we can go ahead and cut E3. and add it to the VSP tree. And then we can again simply reverse the disassembly order as before and get our sewing order. E3, E2, and E1. But in practice, though, we learned that when sketching designs, quilters don't always draw complete edges from border to border. And it turns out that the exact algorithm I just described still works even if we only have a partial input sketch like this. So first, let's label our edges. And now let's see if we can find a cuttable edge. So let's try extending out E3 to the boundaries first. But we find that it has E2 on both sides and therefore isn't cuttable at this point. And likewise, if we extend out E2, it has E1 on both sides, so it isn't cuttable either. So now let's try E1. And we see that E1 has no edges to its right, so we can cut it and add it to our VSP tree. And now we try extending E2 to the new boundary, and it's cuttable, so we remove it. And finally, we can extend out E3 and cut it off. And so, like before, we can reverse our disassembly order to get a sewing order. E3, E2, and E1. So now let's say I have a design like this. And so I can go ahead and I can cut off E3. And I can also extend out E4 and cut it off. But now we see that I'm stuck. So neither E1 nor E2 is cuttable at this point because they both have edges on both sides. So to handle this situation, I'll introduce what are called section edges. So sectioning involves splitting a design into multiple sheets of paper, each of which are individually paper pieceable. However, in practice, joining the sections eliminates several of the advantages of paper piecing, including the precision and stability provided by the paper. So therefore, quilters in practice tend to want to reduce the number of sections. And so we learned about different ways a quilter might choose to introduce a section boundary. And one of these is extending the longest existing edge in the input design. So here, that longest edge would be E1. So this now creates two sections to the left and to the right of E1. And we'll now consider each of these as independent designs. And so we start by extending out E2 for section A, and then cutting it. And now we can extend out edge E2 on section B, and cut it off. So we've now completed the disassembly process, and we're ready to sew back the design. So again, we'll simply reverse the removal process to get our sewing order. So we'll start with edge 2 in section B, and then edge 2 for section A. And then we sew edge E1 to join our two sections. And now we can attach E4, and finally E3. And so now we have our full design. And so, of course, this is not the only way I could have chosen to section the design. And two other heuristics that quilters would commonly use include sectioning along the shortest edge, which would be E2, or sectioning in such a way that we have roughly equal numbers of pieces in each section. So in this balance case, there would be 3 pieces in each of the 2 sections, and if we sectioned again along edge E1. So here we can only section along existing edges, and in the paper we explain how we can find the minimal number of sections using any of these heuristics. So we incorporated these algorithms into an interactive drawing tool that allows users to focus on the visual design while letting the tool handle the tedious ordering step. So here I'll show an interactive session where I'm going to draw a tree. And for that, I'll start by drawing the outline of our tree. And then we'll complete our partial design and see that the result requires no section edges. And then we'll add some internal detail for the tree and complete the sketch again. And we see that even with this added detail, our tree still requires no section edges. And so now we'll add a star to decorate our tree, and completing this design, we'll see that the star adds 3 section edges in blue. And this means that it'll take a little bit more work to sew, but we end up liking the way that it looks otherwise. So then we'll next explore some different section edge heuristics beyond the current draw order. And so those include the longest, shortest, and balance. And we like the balance option best and use it for the final design. So this whole drawing session showed how we were able to check for paper pieceability throughout our sketching process and make decisions about different potential completions very quickly. And this lets us kind of balance adding more detail to our design while keeping in mind how difficult the design might be to sew later. So we and other quilters have created a range of designs using our tool. And they can start with something like a partial sketch, like this milk carton, completed in the tool, and then sew the final result. They can also sketch by tracing an existing image, and then completing the design as they go while adding additional detail, and then sewing the final design. And quilters ended up creating many different designs, such as those with concave shapes, those approximating rounded edges, and those without rectangular boundaries. And quilters have gone on to use and adapt our tools to create their own designs like this, which was created using the implementation the quilter wrote in the programming language R. So when we initially came up with our representation of foundation paper piecing based on faces, we wanted to formalize what had previously only been rough rules of thumb for quilters. And formalizing foundation paper piecing constraints allowed quilters to create their own original designs without having to worry about ordering the faces. However, this representation only worked for complete inputs at the end of the design process. But we learned that quilters often think about edges, and shifting to an edge-based representation enabled some new possibilities for designers. So our new edge-based design representation enables checking whether a design is paper pieceable earlier in the design process, and automatic sectioning, which enables quilters to create more elaborate designs. And so as much as we're personally invested in quilters and empowering would-be designers, perhaps a broader observation here is how a change in the representation of this problem allows for a different type of interaction that better fits with how quilters think and tend to work, which is in a more sketch-based way. And that's something that's critical for building design tools, not just in quilting, but in many different domains. So with that, I'd like to thank you all for your attention, and I look forward to taking your questions. Thanks.
So do we have any questions? Please come here. Otherwise, in the meantime, it's a very fascinating topic, and it really helps designers and people and makers to build something. And I was wondering, at a moment, it helps if you have an image, pretty much like a fixed design, it can help you to transform it into a quilt, right? And I was wondering, could you imagine that in the future, based on the work that you did so far, this could also be something like a creativity support tool? So in the process of getting these quilts, that you can actually do modification and changes in the design.
Yeah, that's a great question. Yeah, thank you. Yeah, so I think that so one of the kind of design decisions that we made was that we're still going to have people kind of lay down the edges themselves. So we weren't just going to take in an image and kind of automatically extract those edges, but that's something that you could definitely do for somebody that doesn't want to necessarily pick where those might go or go through the sketching process. So I think kind of one avenue is, yes, you could go from an image and kind of go down that avenue of taking a more automatic approach to the kind of visual design. And the other piece is you could think about taking maybe there's a ton of traditional designs in quilting. You could think about taking one of those kind of long-standing blocks and then that maybe isn't necessarily initially paper pieced and using the tool to kind of make it possible to sew that way. So I think that there's definitely we chose one avenue of design support, but I think there are plenty of others that you could think about as well to support different types of users. Yeah, thank you.
Jasper from the University of Washington. So, for warning, I have no background in quilting, but I noticed that the quilter was drawing curved sketches, or curved lines in their sketch, and I was curious whether the tool could possibly support curves as well, or is that not possible for some reason?
Yeah, thank you. So in the sketching process, quilters will maybe want a little bit of a curve in there, or they're going to draw something that has rounded edges, and then typically later when they actually go through the process of making the design, they'll kind of even those out into generally straight lines. So one of the kind of constraints of paper piecing itself is that it is generally done with straight lines. Part of that is just having to attach pieces of fabric to a sheet of paper, that just having that give that you would need in a curve just kind of typically isn't supported. So overall, if people want to sew curves, they typically wouldn't use foundation paper piecing and would have to kind of adjust the set of straight lines to kind of represent the visual design that they want. Yeah, thank you.
Hello.
We good?
Hi. My name is Angelica. I am from Carnegie Mellon University. I just wanted to ask, in terms of the tool itself, like I know that probably in design, people typically use a lot of vector-based software, and I don't know if this is something that's typically used in quilting, but have you thought about adding support for people importing their own vector-based images for the interface?
Yeah, thank you. So so currently we have like a web tool where you can upload an existing design or upload an image and draw on top of it. We also sometimes draw our designs like in Illustrator or another SVG and just take that as input and kind of complete the design from there. So that's definitely something that, in terms of on the kind of front end of the pipeline, you could definitely work with those types of graphics for sure.
Thank you.
All right, let's thank Mackenzie once more time. So, and now we come already to the second last project for, I think the second last project like for this session, unfortunately. And what we will hear today about is Project Primrose, reflective light diffuser modules for non-emissive flexible display systems, made by Christine Dierk, TJ Rhodes, and Javin S.P. Miller. And today, we're going to welcome Christine Dierk. Christine Dierk.
There we go. Thank you for the introduction. I'm Christine Dierk. I'm presenting Project Primrose. I won't read the subtitle again, it's very long. But this is work that I did at Adobe Research, working with my collaborators TJ Rhodes and Gavin Miller. So in this work, we present a new material for flexible displays, reflective facts. I don't know why it keeps doing this. Let me try again. I'll try not to touch it. Hopefully we'll keep it. So again, new material for flexible displays, reflective backed PDLC. This low power non-emissive material can be cut to any shape and dynamically diffuses light. And our contributions include key modifications of typical PDLC usage to adapt this material to the new context.
You want to try this adapter?
Yeah, let me.
Because I have to say, Peter is always having those kind of problems.
Thank you so much.
Yeah.
Let's try again. Yeah, I hope so. Okay, we'll try again. So again, key modifications of PDLC, modular hardware and software for controlling the display elements, exemplar artifacts, and interaction modalities. And the good news is most of these clips are later in the presentation, so you haven't missed anything. So in terms of related work, there's growing interest in HCI and beyond to augment traditional textiles with display capabilities. These embedded displays enable novel applications, including empowering personal expression, fostering social interaction, and encouraging engagement with personal data. Perhaps the most common material used in textile displays is the LED. LEDs are low in cost, small in size, and readily available in a wide variety of form factors. However, research in HCI has also explored non-emissive materials for textile displays. Our work is most related to prior works that attach semi-rigid displays to textile substrates. These works leverage electrochromic and e-ink displays. And the power requirements of these display types are much lower than that of LEDs, and they're also visible in direct sunlight. So this is kind of a different experience than what LED textile displays provide. So first, I'm going to talk about the display elements themselves. As mentioned, we use PDLC, which stands for Polymer Dispersed Liquid Crystal, which is exactly what it sounds like. It's liquid crystal molecules that are dispersed in a polymer. And when there's no electric field present, they're kind of randomly dispersed. They scatter light, and they appear opaque. But when there's an electric field, the molecules align, allowing light to pass through, and the material appears transparent. And as you can see, this material is commonly used in smart window applications. Our implementation leverages several key modifications to typical PDLC usage, and the first is that we apply a reflective backing. So the reason for this is that the difference between the two states is significant at a distance, but much more subtle when you're pressed up against the surface. So you can see in this video, it pretty much looks the same in the two different states. So in this work, we use reflective material as a backing for the PDLC, and you can see that the difference is much more pronounced than without the backing. And using this material, we can design a flexible display that has two states for each pixel, either this reflective silver or this opaque ivory. Our second key modification of typical PDLC usage is to subdivide the large panels into small display elements that we refer to as petals. And we leverage laser cutting to cut the PDLC, enabling us to implement precise and intricate petal designs. This is a design we made to kind of resemble lace. And these display elements are driven by custom display modules. Each display module controls 8 petals via 3 analog switch devices. We use octal single pull, single throw analog switch devices to simulate quad double pull, single throw, and one analog switch device creates 2 global bus signals. And combined together, these bus signals provide 15 volts alternating current to the petals because PDLC does require alternating current. And the remaining analog switches control 4 petals each. But for simplicity, we'll just start with a single petal driver and a single petal. The petal has 2 exposed electrodes, the first of which is directly connected to bus. And then the other electrode is connected to 2 outputs of the analog switch, whose state determines whether it's connected to bus or not bus. When not bus is connected, the petal is supplied 15 volts alternating current. The PDLC becomes transparent, meaning that the reflective backing becomes visible, and the petal appears dark gray when you're looking at it. And when bus is connected, there's no voltage differential, the PDLC is opaque, and the petal appears ivory. One thing to note is that this crisp transition from transparent to opaque only happens if the petal is directly driven to the 0 voltage differential. Switching from not bus to not connected also causes the petal to transition from transparent to opaque. However, the transition is much more gradual as the petal naturally discharges, as you can see looping here. And this crisp transition is important because it enables us to implement video frame rates as well as grayscale control using pulse width modulation. The control logic is the same for the remaining petals. I won't go through them all. And the petals are electrically and mechanically attached to the display modules via shield clips. The vertical arrangement of petals enables broad application to a variety of form factors as it allows variable spacing along curvilinear surfaces. Inspired by traditional textiles, the shape of the board is specifically designed such that the modules can be woven together, increasing resolution of the display. And here's what woven driver boards look like on our canvas prototype. The modules are designed to be sewn directly to textiles, and the mechanical design affords flexibility, as well as stretch orthogonal to the length of the boards. And these display modules are daisy-chained using flat flexible cables, also known as FFCs, and connected to an SPI controller. And the display modules could be driven by any SPI controller. However, we designed a custom main board to run ours. And in terms of power, the current draw of a single petal is 0.2 microamps at 15 volts alternating current. So it's very low power. And then the power consumption of our canvas prototype, including the mainboard components, is 70.3 milliamps at 15 volt DC. And so most of this power is from our mainboard, which has not been optimized at all. So this could be much, much lower. But for now, it's still pretty low. It's just over 1 watt. And using this, we implemented 2 artifacts to demonstrate how Primrose technology can integrate into various form factors. First, to explore how Primrose technology can be leveraged in more traditional form factors, we constructed a 2D canvas. The canvas features up to 256 petals controlled by 32 display modules. And the petals are arranged in a 16 by 16 offset grid. This prototype was constructed using a 12 by 16 art canvas. We first cut windows for mechanical relief and component access. The display modules were stitched in place and daisy-chained using off-the-shelf FFCs. And we constructed 4 canvases in total to support remote internships. As mentioned, each canvas can drive up to 256 petals of various shapes and sizes. For the isometric canvas, some of the petals are double wide and not every petal position is populated. So that's how we get 192 instead of 256. And we will have one of these canvases at the Adobe booth during the demo session later today if you want to check it out. We also constructed a bag prototype which features 448 scale pedals controlled by 56 display modules. And this display area wraps horizontally with no visible seams. And the pedals themselves fall into 8 distinct sizes in a 16 by 28 offset grid. And we incorporated variable pedal size so that the pedals would complement the tapering of the bag. So they're more narrow at the bottom of the bag and then wider at the top, which is why you don't really see any gaps between them. To construct this, we first drafted a custom pattern to perfectly house our electronics. Similar to the canvas, this pattern included windows for mechanical relief and component access. We laser cut the pattern pieces out of leather for precise alignment of these design features and hand dyed them before adding a cellulose board stiffener to provide extra structure and stitching the 2 sides of the body together. We then stitched the module boards in place, inserting FFCs to daisy chain and power tap, adding pedals throughout to test and debug. Once all the boards were installed, we added the base and the top binding before populating the remaining pedals. Finally, we assembled the control electronics in the internal compartment and added the lining. And so that's what assembly looked like for the bag prototype. For these artifacts, we explored 2 different methods for content authoring, procedural and frame by frame. For procedural animations, the frames are generated in real time and the pedal index determines the pedal state. For example, the even-odd animation uses a push button to toggle even and odd pedals, and then the vertical arrangement of pedals causes this to look like horizontal stripes. Here's 2 examples of slightly more complex animations, Geo and Parade. For frame-by-frame animations, pixel value determines pedal state. And in the interest of time, I won't go into this, but please see the paper if you want additional details on how we convert animation frames into machine-level code for these devices. Here's some examples of frame-by-frame content on the hex canvas. We also explored 2 interaction modalities, Bluetooth-driven and sensor-driven. As an initial exploration, we implemented several interactions using an IMU. For compass, the displayed content maintains its cardinal direction regardless of the bag orientation. And for twist to update, the user can twist the bag to update the displayed content. Morph combines these 2 modalities. The displayed heart maintains its cardinal direction while rotating the bag inverts the color of the design. And as you can see in this clip, the perceived contrast in the displayed content depends on lighting condition, reflection of the physical environment, and viewing angle as well. And to go a little deeper into that, in these photos, the left half of the canvas is on and the right half of the canvas is off. And as you can see, the lighting and the physical environment were deliberately manipulated to kind of highlight worst case scenarios, including environment reflection, specular highlights, and low contrast. Surface normal also directly affects the appearance of the pedals. Unlike the remainder of the display, the bottom row, where the pedals are slightly tilted, from resting on the row of petals beneath them, the bottom row of petals lies completely flat against the canvas, which gives it a different surface normal and makes it look a little different on the display. The modular nature of our system affords application to a diverse range of form factors, including architectural and wearable implementations, and Primrose could also be used to enable complex curvilinear displays. Please see our paper for additional details and stop by our booth during the demo session if you'd like to see it in action. I'll conclude by saying that we are hiring an intern to implement real-time data streaming over Wi-Fi to these artifacts. So if that interests you, you can find and apply for the role on research.adobe.com. So thank you. And thank you for the adapter.
Really impressive engineering and design work. This is Lining from Carnegie Mellon University. I'm curious, have you thought of using this system for things beyond display? Because display, there's LEDs and other technology. But for example, can the light be tuned to black will absorb solar light and maybe you can use it for heating up the body? Or maybe privacy? Because you can change between transparency and not for a bag or a clothes. Yeah, just curious whether you guys have
those are are great ideas. I'd love to chat more later. One thing we have thought about is kind of not using the display itself, but the reflection off of the display, because if you have a spotlight on it, then you can kind of control the reflections coming off of it. But we haven't looked so much into non-display applications for it.
Thank
Yeah,
you.
thank you.
Hi, there's one question about design tool. Have you considered to design software can simulate for people if you want to which area deform or not, and it can before fabrication they can do that.
Are you talking about content once the display exists, or more
Yeah.
like when you're designing what to kind of affix these modules to?
So have you see or have you considered about it?
We're definitely interested in both of those areas. Right now, we're kind of just using existing animation creation tools to kind of generate 2D animations and then map them to the display. But of course, once you have a more 3D complex, we are definitely interested in what the best way to design content for that complex shape is. And we probably do need some sort of 3D model of the display. We've also thought about maybe using augmented reality to do it. So you could be looking at the actual artifact and then kind of designing content that way. Yes, so we're interested in lots of the content authoring. Right now we just kind of have the basic version, but we're very interested in exploring that moving forward.
Thank you.
Thank you.
All right, thank you, Christine. Super awesome talk.
Thank you so much.
The same laptop, I was like very picky about the connectors.
And unfortunately, we already come to the last talk of today. And the last talk of today will be computational design of active kinesthetic garments by Velko Vechev, Ronan A. Hinchet, Stelian Kroros, Bernhard Tomaszewski, and Ottmar Hilliges. And our presenter today will be Velko. Velko, take it away.
Let's just test this out. Okay, yeah. Thank you everybody for coming to my talk. Yeah, my name is Velko Vechev. Maybe I'll just detach this, or maybe I won't. Okay. I can talk into this.
Just say the menu.
Okay. Yes, my name is Velko Vechev. I'm from ETH Zurich. I'm very excited today to share our work on computational design of active kinesthetic garments. Active kinesthetic garments are wearable, soft exoskeletons that can provide physical kinesthetic feedback on demand. The two key properties of these garments are that they allow freedom of movement and that they can resist multiple motions with a single design like the one shown here. They can support a variety of scenarios such as workplace training, active posture correction, VR gaming with real force feedback when you make contact with objects, and resistance training anytime outside the gym. They consist of three components. The base garment. These are like skin-type clothing, such as a compression shirt. The active components, in our case, we're using electrostatic clutches. These can be turned on to provide resistance at any time. And connecting material. The connecting material is flexible, but it's not stretchable. And let's have a closer look at how the ES clutches work. ES clutches are packaged in a stretchable textile. When they're activated, they strongly resist elongation. And when they are not active, they are fully stretchable along their main axis. So the problem is that when we attach these clutches on the base garment and stiffen them, the garment just deforms, right? It absorbs all the strain. So what we need is a connecting structure that grounds the forces onto the body and supports and transfers the loads. So the question is, how do we connect our active components for both maximum comfort and performance? Our idea is to use a computational approach that uses topology optimization and intelligently places connecting material in a way that optimizes both objectives. And to guide our design, we introduce a new dual objective that takes into account the state of the components, for example, if the clutches are on or off. A recent trend in graphics has been to optimize garments with motion considerations, for example, to reduce friction and pressure. And in our previous work, we optimized for passive resistance for a single motion. And we also take inspiration from systems utilizing electrostatic clutches, our active components. The reason we choose these is that they're very light, they're very flexible, and they can provide extremely high holding forces relative to their size. So in our work, we take a computational approach to automatically design garments with embedded active components. Okay, so we start with the input motions. These are defined using the SMPL body model. And designers then place parametric clutches directly on the pre-made garments. And from this, we automatically create the design for our garment, as you've already seen. And finally, we fabricate the design and connect it with our active components. And you can see here what it looks like for the different motions. And so based on our goal of maximizing performance and comfort, we formulate the following design objectives. We want to maximize the resistance the user feels, and we want to do that from multiple motions. We want to be careful about where we put the connecting material. We don't want to restrict people when they're wearing these garments. And these design objectives all require very careful placement of the connecting material and an understanding of how the garment behaves as it moves over your body. And satisfying these objectives is actually a very difficult design task for users, which you'll see later in our studies. Okay, let's first consider the objectives of maximizing resistance and minimizing the impact on range of motion. Just gonna take a sip. So let's have a look at how our automatic design method optimizes for both of these objectives simultaneously. Here, the green lines represent the material coverage. It's reducing over time. The blue line represents the energy of the garment when the clutches are on, and the red line when the clutches are off. As the optimization progresses, we observe a gap between these two energies, and this is an energy differential. This is what we want. This is what we're aiming for. It's the key to the solution. And we see in the final design that in the on state, there is a large amount of light blue and yellow. Here, I think it's on the right side, that side, or your left side. And in the off state, we see that the garment is mostly dark blue, which means that it is low in energy and it's easy to move in. And we describe these states by energy terms. E of x star is actually a result of a simulation. And given the design vector D, which describes which parts of the garment have connecting material and which don't. Okay, so we formulate this as an optimization problem. We combine these two objectives. So I have to emphasize here, what we're asking is super counterintuitive. We're saying make this garment energy dense, but also make it not energy dense at all, right? So really the only way to do that is by taking into account the state of the active components into the formulation. And this allows us to optimize for our two design objectives. This is like highly simplified. You can get more technical details in the paper. And to satisfy our last design objective, to resist multiple motions, we extend our formulation by summing the energies of the garments over all the motions. And again, we've omitted some technical details. I just want to mention that if you want to balance the material across the different motions, you have to apply a kind of normalization on the material. And you can see the paper for more technical details. So with this formulation, we can now optimize for resisting multiple motions. And let's have a look at what this looks like in action. So the resulting design for each of the three motions. And so the first thing we want to notice is that how each of the motion lights up a different load path. It's a bit hard to see in the front, but. And the other thing we want to notice is that all the material kind of routes through the clutches, through the active components, and this is the property that allows us to actually turn on resistance. We created three designs using our method: a 3-motion shirt, a 5-motion, two-motion arm sleeve, and a 5-motion long sleeve shirt, which shows that we can scale up our method to many motions and active components. We selected the shirt and the arm sleeve for fabrication and further evaluation. In our evaluation, the key question we're asking is, and something you might be wondering, is how do our automatically designed garments compare against manually designed garments? In other words, do we really need an automatic method to design such garments? To create the manual garments, we recruited 6 participants, 2 of whom were experts in structural optimization. They used our tool to assign connecting material on top of the garment. The clutches were already placed for them, so they just had to connect them. And they did a design for the t-shirt and the arm sleeve. The amount of material is the same as the one we used for the automatically designed garments. So here we show the comparisons in simulation between the automatic versus the participant t-shirt designs. Our metric here is energy density of the garment. So in other words, the resistance for a given amount of material. And the results show that our automatic designs provide 2 to over 10 times more resistance for a given motion than the manual designs. And you can look at this table, the numbers are not like made up, so there's massive differences. And the question is, why are the manual designs performing so poorly? The insight is that the more motions that you have to resist, the less material you have to allocate per motion. And what our automatic method does, it addresses this by placing material such that it is shared efficiently between the different motions. And this actually is super hard for users to do. Okay, so the next part, we wanted to physically validate things, and so we fabricated 2 of the manual designs, 1 shirt and 1 arm sleeve, and we compared them against the automatic designs using a force sensor. So we didn't put clutches here. You can see that's not a clutch, it's a force sensor, because we only want to evaluate the effect of the design, not the clutch. And the results are actually quite similar to the ones in simulation, showing that our automatic designs produce from over 2 to over 4 times as much resisting force compared to the manual designs. And so given that a single 15-centimeter clutch can produce, it's up there, in excess of 100 newtons of resisting force, what becomes apparent is that the actuator is not the limitation, the design is the limitation. In the case of wearable kinesthetic feedback, the grounding of forces is actually a critical for good performance. Finally, we conducted a VR pointing study where the goal was to impede the user from reaching a target in space using only their upper body. They just kind of reach for the different targets, and we placed the targets such that each target elicits a different motion that the garment was designed for. And we compared the feedback from manual designs, automatic designs, and there was also no feedback mode. Our measure here was how long does it take for users to reach target from start to finish and back. Again, the results showed that automatic designs have a significant effect on performance, denoted by the star here, in particular for the raise and bend motions. And the surprising result here is that the manual designs perform no different than the no feedback baseline, and actually several participants mentioned that they don't feel anything with the manual designs. And the takeaway here is that our automatic approach actually makes the difference between a system having clear or negligible impact on user performance, user motion. Okay, so in conclusion, we introduced a state-dependent objective for on-body topology optimization with active components. Our studies show that our automatic designs are efficient across multiple activation modes. And there is potential here to impact wearable haptics and sensing devices even that need to be grounded onto the body. The future work, we could look into the clutch placement, which is currently manual. You have to pre-place the clutches. And we can also take into account more fine-grained control strategies, since currently we optimize with respect to all the clutches on or all the clutches off, not individual control over each clutch. So that wraps up our presentation. Thank you so much for watching. I would like to acknowledge our Hasser Foundation and ERC for helping to fund this research. And also, there is a takeaway from this slide, and that is that I'm open to job opportunities and internships, so talk to me afterwards. And also, one more thing. We don't have a demo. Of course, I am wearing one of the kinesthetic garment shirts, so feel free to come and talk to me after to check it out. Here it is. You can, it might be... It's not so hard to move in, you know, a little bit awkward, but yeah. Okay, thank you.
Hi, this is Andre from KAIST. I'm just curious if you have to have, as a basis for the design and for the optimization, 3D scanning of the user. And if that's the case, how much is this generalizable? Like, let's say you want to do an haptic device that actually can transfer to another person. Do I have to scan this person in order to do the optimization?
Thank you for the question. Good question. Yep. So this is kind of in the direction of personalization. We use the SMPL body model, which is very easy to fit to 3D scans or like using Kinect sensors. In terms of designing one for having a design generalized across different shapes, I think there would be depending on the body size and depending on the change in body size, it could require a different garment. But there is a little bit of leeway because the actuators, the clutches, have a little bit of give, but some parts of the garment are stiff. So if you have like huge arms or small arms, we should make a custom garment for you, and it's possible to do that. Thank you.
Megan Hoffman from Northeastern. I'm going to follow up on that question a little bit and
chose to use a compressive garment for the kind of base material,
Yeah.
which means it's going to fit very closely to a person. But is there a way to kind of work without that very close connection to the human body? So could you use something that had a little more ease or was maybe a little more fashionable but was still tight in the right regions? Is that something that you've considered or kind of thought about?
Yes, actually, we had some fashion designers like reach out to us about this work. If you want to consider looser clothing, basically this is very easy to simulate, like the garment the garment on body model. If you want to consider looser clothing, you need to have a little bit of a more advanced simulation model for the garment, and maybe you would also have to consider dynamics over time, because our model only solves statics, like it's a static equilibrium. So you would have to kind of figure out how the garment changes over time during the motion and how it moved from the start to the finish. Thank you.
Steve Fine, Columbia University.
Okay.
So your system way outperformed the humans. But did the humans just do it on their own? Were they able to see, for example, some of the results produced by the expert system? And I'm wondering if they saw a set of different things your automated system did, could they kind of learn some basic approaches that maybe would allow them to perhaps do as well or maybe better now that they've been seeded with this sort of expert performance?
Yeah, okay, thank you for the question. Good question. Let me think for a second. So first, our tool, it's not something we presented. We have a tool that kind of shows you the simulation as you're kind of placing the material, so you have a little bit of feedback. It's not something we wanted to focus on. We didn't show anybody the automatic design, of course, then they would be biased. That would not be good. We did have two people. I have a backup slide, so for the designs that people made, and actually the ones with the star or the expert designs, and you can see they're experts in structural optimization. They create things like structures that are a little bit more, they understand how the loads move throughout. But yeah, as we have 3 motions. We go up to 5 or 7, degrees of freedom on the body. It becomes very tricky. And I think, maybe if you make 20 or 50 of these, you can get good. But just run the algorithm; it'll do it for you, kind of, or at least help you to get a starting point. And you can modify it.
Whether their modification might go better.
You can also see how it works, right? You can resimulate and see how your modifications impact.
Thank you.
Thank you.
So let's thank Michael again. Great presentation. All right, and with this we are at the end of today's session. Many of the projects that you've seen today will also be in our demo session tonight, where you can try them out directly. It officially starts at 7 p.m., but many of the demo presenters will also be there a little bit earlier. So once you grab your food, feel free to wander around and test all the demos that are already up. All right?
Oh my.
What's the other one?
This one, but it says it has no output.
No,
control.
the virtual one?
It usually, I don't know what that one is, but I don't think that's the right one.
Maybe try.
Let me see if I can.
No, I think this one is correct. It's just like we need to find a place to control.
It should be that one. That one should work.
Yeah.
Can you try plugging it in through here?
Oh, okay.
Yeah, like that was what was working with all the other laptops.
Oh, I think it
But
looks.
it's like I think
still.
it's the cable.
No,
Did
no,
it
no.
work?
This connection are all good. It's
Yeah.
just that you need to control the output side.
Yeah.
And the output
But I
side.
don't know.
There's probably a
Should
controller
I
or something.
try another computer? Should I try another computer to?
No, I don't think that's a computer's problem. It's just that the sound for the projector, that is not working.
Yeah. Tech support.
I don't have this one downloaded. Though.
Yeah, I can airdrop it.
Okay.
Or you know what? You can just use this microphone. You use your
Yeah, that's
laptop.
one option.
Yeah.
Let's just see if this works.
Yeah.
Let's just, look at this lightning talk. Okay. No, stop it, sound. HDMI, no, it still doesn't work. Yeah, so maybe if you just use, I feel like it has to do with the.
But it didn't play any sound with the muting microphone.
So all of this audio have to go through this?
Microphone microphone, possibly, because I don't know if the cable is actually like working.
There should be a controller or something.
I didn't see. But yeah. No, like the computer didn't play the sound.
Computer's not playing the sound.
Yeah, building,
What?
right?
You
Yeah.
need to change to the built-in.
Yeah,
Yeah,
so
I
that
changed
should
it to
work,
the
and it's
built-in.
not playing sound.
Yeah, it's
Can
not
you
playing
try?
sound.
Can you just try again?
Go to the
Presentations.
yeah,
Oh,
sure.
okay, it's working.
There it is. But you might want to like this.
Okay.
Try.
To let them propose the.
I plan to build on this research so we can go beyond traditional ways of interacting within a fixed level of abstraction and unlock the full potential of human intelligence.
Yeah, this one is actually.
I love to network and discuss any job opportunities,
No, I
so
think
please.
this one doesn't work.
This one doesn't work. Yeah, this is not working.
This one is working. Can I try the?
Yes, please.
Let's see if this is power protected. It
Oh,
doesn't.
okay, that works. Nice.
Here, let me. I don't know if my.
There we go.
Okay, well.
You wanna?
The other thing, just watch out that like there's no power thing connected to this.
I know.
So
Yeah.
it's just gonna burn through your. So we might want to just
Probably
run
fine.
through.
Do you have audio? No.
That is. It's okay.
Oh yeah, they will use this.
Okay, let me see. Oh, but it's not gonna play audio allegedly.
Audio you need to set up.
No, they literally just took the mic into
Yeah,
place.
yeah.
Let's see if that's gonna work.
Okay.
Oh, fantastic.
I always share the same microphone, which is awkward, but that one also does work if I just get sound.
It seems to work.
I think I will.
Here, try.
Try this. Let's try this one. Oh no.
Actions available. Size 171.7 points wide, 26.3 points tall. Position 19.1% from left, 80.
Okay, I think it's good. Okay. Good.
And also for your talk, once we start the Q&A for the previous one, you can come and set up.
Okay, sounds good. What is happening? Okay, return. Display. Inside.
let's get started. Welcome everyone to the session, Information and Visualization Interfaces. My name is Bo from the University of Michigan, and I'll be chairing this session. So in this session, we will have 6 amazing projects on making information powerful through interfaces, which includes ways to collect and forage and organize information for sense making. We'll have them for analyzing information for generating insights. We'll be able to link them to author interesting applications, as well as visualize them to improve physical rehabilitation, as well as compare and describe them for digital accessibility. So we look forward to a very interesting set of papers. And before we get started, we'll have 2 lightning talk videos that will play by Sang Ho and Yi Xia from UCSD and Shanghai University. Please.
Today, many aspects of our lives and the tools we use are driven by abstract domains such as data and AI. My research aims to make them more accessible with dynamic and layered representations that would allow people to explore, discover, and interact with appropriate levels of abstraction. To this end, during my PhD, I studied how to design layered representations. Specifically, I formulated the idea of coding strip, a form of layered representation with code and corresponding comic, and then I used it to study how to design, use, and create layered representations. I plan to build on this research so we can go beyond traditional ways of interacting within a fixed level of abstraction and unlock the full potential of human intelligence. I would love to network and discuss any job opportunities, so please feel free to reach out.
Hello, I'm Yi Xiaokang. I'm an undergraduate student from Shanghai Jiaotong University. My major is software engineering, and currently I'm looking for a PhD advisor. My interest is human-computer interaction, including mixed reality, wearable, and education. In UIST 2022, I worked with Professor Xu Boyang and proposed a hybrid tangible AR souvenir to create an interactive visiting experience. I also work with Professor Stephanie Miller in MIT on the reprogrammable photochromic fiber. I built a user interface with processing and a simulating system with Python, OpenCV, and Arduino. I also researched virtual reality and haptic. We proposed a novel retargeting solution for a task of grabbing and placing objects in virtual reality. I worked with Professor Chaoping Chen and presented a method of simultaneous tracking, tagging, and mapping for augmented reality. I'm the official designer for IE VR conference, and this is my exhibition in Shanghai. Please contact me if you are interested in my research. Thank you.
Awesome. Let's have the first presenter set up, please.
Do you know how to full screen this? Sorry. Do you know how to like fully full screen this without the right, this whole thing?
I think there's an option for full screen.
It's just on Google Slides.
Yeah.
Does that make sense? Okay. So this is the presenter view.
Yeah, I think if you just drag that tab into a separate one, then it's big enough. Yeah.
Looks like this.
Can you drag any more? There's a button. It's full screen.
Gotcha. presenter view. Okay. Oh, perfect. Thank you.
All right. So for our first paper, we'll have Matt Nguyen-Pong will present work with collaborators from University of Colorado Boulder as well as UNC Chapel Hill. So Matt recently also moved to UNC Chapel Hill, and he will present work on Scholastic, which is a human AI collaboration system for interpretive text analysis. Take it away.
Hey. I was told that masks were required at this conference, so. Can you hear me well? Is this mask, should I face this towards me? Is it supposed to be like this?
That is so if you have audio from your computer.
Oh, okay. Do you guys hear me well? Okay, cool. All right. Okay. Perfect. Oh yeah, I was just kidding. Thank you for coming to our session. This paper is about supporting inductive and interpretive text analysis with visual analytics. Say that 3 times fast. You might be more familiar with the terminology qualitative data analysis. To illustrate a use case for our tool, I wonder if you've ever been on a food blog website and noticed that all these recipes seem to contain flowery details about the bloggers' personal lives, and wondered to yourself, I mean, besides for search engine optimization, why are these stories so long? Has anyone studied this? What stories about interpersonal relationships or certain food items likely to elicit within recipe blog posts? And to answer this, you might scrape this website into a CSV file. And from an interpretive approach, analysis will entail manually coding excerpts on this data set and grouping those codes into categories. And you might use Google Drive to conduct this analysis, or fully fledged tools like MaxQDA. The point here is that interpretive approaches are manual and very time-consuming. But at the very least, because it's manual and interpretive, we can ensure that human expertise is imbued in the analysis. Whereas algorithmic approaches to study text data using topic models or document clusters can generate insights automatically. That's VizSpeak right there. But that's never the full story about machine learning. It still takes a human expert to interpret these models, validate them, and refine these models so that to ensure that they address the research question at hand. So in building our system, we speculated, what if we kind of inverted this paradigm? Instead of having a human in the loop workflow to analyze text data, what if an interpretive researcher sampled and coded documents, categorized those codes, and the model can then learn from their analysis, and the visualizations of those models can help users sample and code documents further, thereby placing the machine in the loop of qualitative data analysis. Our system comprises 3 views: the document map, which supports breadth-first exploration of the data set; the document reader, where the analyst highlights and codes documents; and the code examiner, which is used to iteratively refine codes and categorize them. Our system embodies 4 major design considerations. First is to support human expert induction, and the second is to have the model learn from the human's analysis, all the while using analytical paradigms that are familiar to an interpretive researcher, and finally overlaying those codes and categories onto the model visualizations. First, let's see how the document reader and the code examiner view support expert induction. Using the document reader, the analyst highlights and codes documents, and they also choose code keywords, which are a subset of the highlighted words that were the most semantically meaningful to this code. In the code examiner, the analyst then refines these code labels by revisiting previously seen documents in context. They can then also create and reassign categories for these codes. And here you see an indented tree depicting hierarchical word clusters generated from text data. And this is a prune tree that reveals only clusters related to those code keywords. So by clicking on each clusters at various levels of the hierarchy, the analyst can sample 30 documents that are the most potentially relevant to this code, again, in order to iterate on the user's ongoing analysis. And after a round of analysis, we will see how the machine can then learn from the user's codes and categories. As we saw, using the code examiner, the analyst refines codes and categorizes them. In the navigation bar of Scholastic, these codes are persistently shown, colored according to their categories. And here we will also find a button that says Update Clusters. Once the analyst clicks this button using the category tags, codes under those categories, and the code keywords, we then constrain how the words are clustered together and subsequently how the documents can be clustered together. And this entails running a community detection algorithm on this multi-layer network. This algorithm is thus interactive and hierarchical. And it adapts to users' ongoing analysis on their demand. It also outputs hard clusters instead of requiring the user to set a minimum probability threshold on topic models to output hard clusters. And it clusters documents along with words simultaneously. Once the models are updated, they can continue to sample documents using these models. So here we see the document view, document map view, where the colored pins indicate documents that have already been coded, and gray hexagons indicate documents that have been visited but not been coded yet. Using the step slider on the top left, I can adjust the granularity of the hierarchical cluster visualization, and also step through the evolution of these clusters as the model adapts to user input. And if they choose not to sample using the visualization, they can keep on sampling a random subset of the data. But using the map, right-clicking on the document shows a preview on the right, and left-clicking on the document takes the analyst to the document reader, where they can analyze its text. And we can see how all this works within an analytical paradigm that are already familiar to qualitative researchers. Even though existing interactive modeling tools can help users understand the data breadth and allow users to incorporate expert knowledge using interactions, they require that interpretive researchers to learn how to use these tools and work outside of their existing workflows where they label text data with codes. Whereas in our approach, the model learns naturally from the user's ongoing analysis using their codes and categories. Using familiar paradigms is also inherent in the visual design of our tool. Our document map draws a familiar visual metaphor to navigation maps, and the code examiner view draws a visual metaphor to familiar file folder structures. Lastly, we wanted to overlay codes and categories onto the model visualizations. To illustrate why this might be useful, let's go back to our illustrative user scenario. The research question here is, what stories about interpersonal relationships do certain food items elicit within recipe blog posts? Now, this is a question that actually requires multiple levels of analysis. So at the content level, the document clustering algorithm can help us organize all the meat recipes into one group and all the cookie recipes in another. And if the user finds that the top cluster tends to contain narratives mostly about feelings of warmth and community, and the bottom cluster tends to contain stories about family, it helps to be able to compare and contrast the model outputs, the codes and categories, and draw conclusions about the data, such as meat recipes tend to foster stories about warmth, and cookie recipes tend to foster stories about family. To summarize, in our tool, we executed the vision of placing a machine learning system within the loop of qualitative data analysis. And we accomplished this using an incredibly parsimonious input strategy, which entails the analyst coding documents, specifying code keywords, and categorizing codes, which one of our study participants noted that that's really a thing that they would be doing anyways. And in our paper, you will find a summary of outcomes from 2 qualitative researchers using our tool to conduct analysis. But to summarize directions for future research, we note that approaches to interpretive text analysis can vary widely. And this variance can be a function of the data set or as a function of the research question itself. And we envision that future system work supporting qualitative research using machine learning and visualizations will be able to better adapt to these various user needs. Thank you to my collaborators and my former colleagues at the Atlas Institute, University of Colorado Boulder. Thank you.
So for Q&A, please raise your hand and I can give you the mic, or you're welcome to come to the front as well, either way. Any questions?
Hi, Jasper from the University of Washington. Really interesting work. I'm curious how, when you're designing the machine learning interventions for qualitative coding, like I guess I'm thinking in the back of my head, like grounded theory, for example, existing qualitative methods have very established and strict process.
Yeah.
So how does this tool interface with, I guess, those existing conventions?
Yeah, well, we try to focus on really the coding and categorization processes that are really inherent to all these methodologies. And really there comes a question where, for example, like when you summarize findings and talk about, oh, we use grounded theory and workflows like that, how do we talk about using novel systems? I think that this tool is really meant for like the initial stages of organizing text data into the initial codes and categories, and ultimately can be potentially generalizable to those methodologies. And I think that right now, this interpretive research communities are seeing the benefits of machine learning to be more amenable to these mixed initiative approaches. Yeah.
Thank you.
Thank you.
Any other questions? Well, please, the next presenter, please set up.
Thank you.
Hi, Joseph Chang from Semantic Scholar. I guess a similar question. So when you do thematic analysis and grounded theory, a lot of times you're trying to find these patterns and sort of have some perspective about what's important. So if you're doing clustering, do you think there's a risk of like imposing some structure or perspective on the person doing the analysis?
Yeah, so it's important to note that the models are being used for sampling. And really, sampling bias is going to be inherent to no matter how you approach the data set in qualitative data analysis, I think. You can do it manually or you can use these machine learning models. Again, I think that we're at a place where interpretive research mostly understands that these tools can help organize data at scale. So I think it comes down to really just saying, oh, this is how we use machine learning to organize text and begin kind of the analysis.
Thanks.
Cool. Let's thank Matt once again.
Next, we have Tarfa, who previously was at MIT CSIL, just recently graduated and moved to Google as a research scientist. So we'll be presenting work done with collaborators at MIT on combining, linking data across the web to be able to create interesting applications.
Thank you so much. Hello, everyone. Thank you so much for attending this session. I'm really excited to be here in person to present my tool, Wixibit. Wixibit is a tool that allows people to author HTML applications that link and integrate data from different websites. I did this work with Leah Veru and David Karger from CSIL MIT. All right. So as we all know, there's now tons of interesting data on the web that people would like to have access to and make use of. But many of this data today is really trapped behind these websites. Now, some of those websites allow us to interact with that data and use it in a particular way through their web pages, but sometimes people want to use that data and interact with it in a different way. And indeed, many of these sites today offer third-party access to their data through web APIs. However, as we might all know, to use these APIs often requires significant programming efforts, which limit the people who can take advantage of them to only a small group of skilled programmers. Now, several prior work have tried to democratize access to web APIs and make it easier or simplify building applications on top of these APIs, including actually a tool that I presented last year at UIST. And the tool is called Shaper. So Shaper does standardize the types of data that we can access on the web, and it does help or allow users to build applications for browsing specific types of data. For example, this application allows people to search and play videos from both YouTube and Vimeo at the same time. However, there are tasks that really involve the integration of many heterogeneous types of data from several websites. Now, this application that you're seeing here is actually displaying videos for the artist Lady Gaga. And obviously, there are tons of information or different types of information about this artist other than her videos on the web. We can find her movies on IMDb, her music on Spotify, and much more. Now, if you want to use a lot of this data about this artist and build a single-page application, for example, that would show the artist information, her music, and videos, and maybe an IMDb-like page that would show information about her movies, then we will actually have to write code that performed 33 HTTP requests or API calls. And we would have to integrate that data from 7 different websites. Now, these types of application reveal another challenge with web APIs, which is entity unification, where for a given entity on the web, like this artist, there's like different types of information about them scattered across several websites, and there's not really an easy way to fetch and integrate that data about a given entity on the web. So why is this really complicated? Well, the reason being is because these connections and links are semantic. They're not actually real. So where can we actually find these links and connections that no other website is interested in providing? Well, we can actually find them in Wikidata. So if you're not familiar with Wikidata, Wikidata is a companion to Wikipedia. It is a knowledge base with more than 100 million data entities on the web that anyone can access and edit. These entities can be about people, places, or anything else that you can think of. And these entities on Wikidata are connected, which some of you might know about already. But what you might not know is that for each one of these entities, Wikidata provides links that represent that entity on hundreds of other websites. And giving those links and connections provided by Wikidata, we built Wixibit to kind of create bridges between objects from different web APIs that describe or represent the same entity. So Wixibit uses Wikidata as a universal join table to cross-reference entities across different web APIs. And it uses Shaper, which is an API access layer tool that we've built and presented last year in UIST, to access the data behind these APIs. And finally, Wixibit extends Mavo, which is an HTML templating language, to support custom properties that would hold the data returned by these web APIs. So using Wixibit, we were able to actually create a number of applications that access Wikidata and other data sources on the web. And each of these applications that I'm showing you here was created by authoring a single HTML document and without any additional programming. And in the next couple of slides, I'll be showing you a couple of demos of some of these applications that we've created. So this is an art gallery application that allows you to search for a painter and browse their paintings. Another application is a game to guess the names of the countries from their flags and other data about them, with the data being read from Wikidata. And this is an artist application that would show you general information about the artists, their music, tracks, and videos. So how does it work? Well, we've created this JavaScript library that understands few new attributes, and you can kind of include it in the head section of your HTML document. And now I'll show you how to use this library and its new attributes to create this gallery or art gallery application. So we first need to enable the library functionalities using the MV app div. Second, we need to connect our application to Wikidata. Now we need to tell our application what we want to, that we want to get paintings from Wikidata by specifying the type of items we want to show and in which language. And then we want to use this input property in order to collect the name of a painter that we would like to show. And here where we describe a template for each of the paintings that we would like to display. And we do this by specifying which Wikidata properties that we want to include, in this case the label and the image, and how we want to show them. And if we want to display multiple paintings, we use the MV multiple attribute that will make a copy of the template for each of the items or paintings that we are displaying. So now this application displays data from Wikidata, but what if we want to integrate data from other websites as well? Well, let's go back to our artist application. Now, to be able to build this application, we want to fetch data from, or general information about this artist from Wikidata maybe, their albums and tracks from Spotify, their videos from YouTube and maybe other video sites, and their upcoming events from Songkick. Now, Wikidata provides general information about the artist, but it doesn't actually provide data about their music, videos, and events. But as I mentioned earlier, what's really cool about Wikidata is that it provides external identifiers for this artist on all of these other websites. And giving that Wikidata item links to these external sources of data, it does provide this notion of uniform identifier that our tool Wixibit uses to query the APIs of these websites to fetch more data from them about this artist. So now using the Wikidata ID, or actually any ID that represent this artist, Wixibit uses these identifiers to fetch the data about this artist from all of these different websites. So if there is a Spotify artist ID, for example, provided by Wikidata for this artist, Wixibit uses this ID and query the Spotify API, and then it provides the user with the Spotify artist property or object that is filled with all of the data or properties that are returned by the Spotify API. And similarly, if Wikidata provides a YouTube channel ID and a Songkick artist ID, Wixibit will use these IDs and query the YouTube and Songkick APIs and defines a YouTube channel and Songkick artist properties that contains the return data from the YouTube and Songkick APIs respectively. Wixibit really made it possible to interact with many web APIs at once and navigate from object to object seamlessly without even realizing that we are moving from one website to the other. Now, to evaluate our system, we actually presented Wixibit in one of the Wikidata conferences, and we had a really great feedback from the Wikidata community. As part of that conference, we conducted a workshop where we asked participants to build their own applications that access Wikidata and other sources of data connected to Wikidata. And we also conducted a lab study assigning users a number of tasks, and one of these tasks was asking the participants to build an application from scratch. The average time that participants spent to build an application was only 5 minutes. Now, I do have to say that we did provide our participants with documentation for Wixibit and a bunch of demos that we have where users were able to view those demos, copy the HTML code. They were able to also fork and modify these code to create their own application, which obviously made it much easier for them to learn how to use the library and get a faster start using the tool. Just to finalize this, we are currently working closely with some of our participants to support some of their real-world use cases of Wixibit. Our participants indicated that Wixibit could be useful for a number of purposes or various purposes. One of them is for educational purposes. A couple of our participants were professors. One was a digital humanity professors who are teaching humanities students who don't really have any technical backgrounds. They do teach them HTML and CSS as part of the class, but in terms of fetching and getting data, they actually copy and paste the data from different websites to be able to view them in their website. So they're currently using our tool in their class to allow their students to basically get the data only using HTML from all of these different websites. We also have another data journalism professor who is also interested in using their Wixibit tool in their class. Other use cases was some of our participants built tools using the Wikidata data, but obviously it's not really easy to integrate other data from other websites with the Wikidata data. So they're interested in using Wixibit to be able to integrate data from other websites into their tools. Other use cases was a lot of users wanted to kind of explore the linked data, whether it's within Wikidata or other sources of data. And this was an easy way for them to kind of visualize how different data sets are connected across different websites and share with their friends and coworkers. And lastly, we had a bunch of Wikidata editors in our user study. A lot of them are editors for a specific type of data, like for example, music or non-governmental data. And they really wanted to, some of them actually hired developers to be able to build pages to show that data that they're editing and working on in Wikidata to create websites for that. And then now they're currently using Wixibit to enrich their websites with more data sets. And with that, thank you so much for listening, and feel free to use our tool.
Thank you. Conrad Lempert, HPI. I really like this. I would
Thank you.
like to use it. Do you think it would be possible to automatically find the relevant data for a certain entry and to build the web page automatically?
That's a great question. So we do have, so in our documentation, you can actually do that. You can actually specify the properties that you're interested in, and we can tell you what are the different data sets from different websites, but it won't be able to build this like nice looking application for you. So you do kind of have to like pick, mainly because there are tons of data or properties for every single entity. So you kind of like need to kind of pick. So in our documentation, we have this code generator where you can like specify the kind of data that you want to get, and we tell you what are the properties that you can get, whether it's within Wikidata or outside of Wikidata. But you have to kind of choose because there are tons of them, and it's not gonna look nice because we don't have the CSS for them. But that's a great question.
Okay,
I can imagine that we can do much more work on actually kind of like guessing what the user is interested in or helping them choose the properties that they're interested in an easier way.
Hi, I'm Jasper again from the University of Washington. Super cool. I actually just
Thank you.
discovered Wikidata a couple days ago, and it's like
Awesome.
really cool. And so it's cool to see this build off it. I was actually curious. You mentioned bringing this work to kind of another audience besides the UIST audience, which was like a wiki conference, and I was curious actually like what they thought of the work and what they wanted to see most as, I guess, as non kind of computer scientists.
Yeah, that's a great question.
All of them.
Yeah, that's a really great question. So a lot of the people in the Wikidata community, which is reasonable because it's kind of like a new, knowledge base. Not really. I mean, it started in 2012, and most of the work that they've done was trying to make their data, improve the quality of their data set, as opposed to actually make it easier for other people to use. So now, I mean, they do have the query service, which you might have used. I mean, it's, a SparkQL, but now they're trying to create, like a friendly, user-friendly interfaces for people to query their data. In terms of like building applications, they have tools. They have a page for a list of the tools that developers have built, but only developers are able to do that because the only way to access their data is either, the SparkQL or the API. So they were very excited about this work because, like you said, there are a lot of people who don't have the technical background, but they're really interested in the Wikidata data. And they found it kind of interesting that not only we're helping people build applications on Wikidata, but we're also taking advantage of like the external identifiers that they're providing and making use of it to connect Wikidata with other sources of data. Yeah.
Thank you.
Thanks for your question.
Awesome. So while Michael set up, we'll have one more question. Very nice talk. My name is Brahman. I'm from Adobe Research. So I'm just curious about the experience for the system. So what kinds of domain is the system most useful? Because I imagine some domain will have difficulties, some domains will be extremely convenient. So yeah, just asking for the experience.
No, I appreciate your question. What domains? So in terms, the only answer that I can give you is basically from our user study or the participants that they use the tools. I mentioned, for educational purposes, that would be a great tool for people who don't have the technical background, but they do want to, make use of the data out there for whatever purpose they have. I mentioned digital humanity, data journalism, and other fields. But a lot of the Wikidata editors or Wikidata users who are interested in specific type of data, some of our users were interested in music, others were, like I said, non-governmental organization. So there are specific people who are interested in specific types of data within Wikidata and other data connected to it. And I think WGZibit would be a good tool for them to kind of like get started with making use of that data that they're editing and using. Thank you.
Let's thank our speaker once again. So next, we'll have Michael Xieyang Liu from CMU HCII, presenting work with co-authors from CMU as well as alum from now at AI2. And this is a very interesting technique that kind of leverages how humans are already kind of moving their cursors around to be able to collect information on the web.
Cool. All right, thank you, Anhom, for the nice introduction. Good afternoon, everyone. I'll present our paper, Wigglelight, Low-Cost Information Collection and Triage. My name is Michael Xieyang Liu, and this is joint work with my awesome collaborators, Andrew, Yansum, Joseph, who's here, and my PhD advisors, Nikki Couture and Brad Myers. We're from the HCI Institute at Carnegie Mellon. So in this talk, I'm going to talk about capturing information, or specifically capturing information when performing sense-making activities online. So the scenarios could be consumers conducting comparison shopping, it could be patients researching their recent medical diagnoses, or it could be developers looking for code or solutions online. When people are doing these kind of tasks, they frequently try to collect some information that they think are useful or important for later use. But what if you're trying to actually learn and also make a decision afterwards? For example, to buy a new camera, which I just did, we might discover many different options from various websites while trying to prioritize which one best fits our expectations or use cases, and also looking for review articles and photo samples maybe that speak either positively or negatively about those cameras. And as you probably have guessed, just collecting information isn't quite enough here. So research showed that in these circumstances, people also want to triage the collected information, or put it in another way, keep track of their sort of mental judgments. For example, if it is a pro or a con, or what we call valence, or it could also be whether I should put this information on top of my stack to follow up on, or it should really go into my back burner, aka the priority. However, if I try to keep track of everything using, let's say, Google Doc, or any other typical note-taking app that people normally use, there is a very high cost and a lot of interruptions involved. As you can see, like copy-pasting information, collecting evidence, taking screenshots, putting them in a doc, and then typing out my thoughts about it, and going back and forth. And what if you need to do all of these on your phone, right? If you think about it, we need to sort of do a long tap, and then drag the two handles to specify how much content you want to select, and then you copy the text using the pop-up, then switch to a note-taking app and put it in or paste it in, and then type your thoughts and opinions, and then after all these, you need to context switch back to where you were and try to reorient yourself. And indeed, recent survey showed that even though participants do sort of these sense-making stuff a lot using their phones, they're not happy with their current process of selecting and also saving content, let alone capturing their mental models or judgments afterwards. So to summarize, with the amount of information we have to process today and the limited tool support that we have, it is cognitively and also physically demanding for us to collect and triage information when performing sense-making tasks on mobile and desktop devices. And as a result, people usually just try to keep everything in their head, which, believe it or not, could quite become, intractable. And most of the prior work on making selections or copying content easier doesn't really address this additional need of people wanting to triage the content right after collecting it, right? So instead of having to do all of the clicking, dragging, context switching, what if we can make this process dramatically simpler and easier? So in this work, we propose an interaction technique where the user only needs to wiggle their mouse cursor over the desired content back and forth for a few times to select and save that content, as you can see on the screen, hopefully. And if they would like to encode their judgment of that content, for example, if it is pro or con, they can naturally finish the wiggle gesture by swiping left or right. I'm doing it backwards. This encoding of the valence information was actually heavily used by our participants in our evaluation. More on that later. And the nice thing here is that we can also map the amount of mouse travel to, let's say, the degree of the valence, like what is shown on the screen here. In addition, we can also sort of take advantage of the vertical dimension by ending the wiggle with a swipe upwards or downwards to encode, say, how urgent it should be, or how urgent should we follow up on this topic, aka the priority, like I mentioned. And again, by taking advantage of the amount of mouse travel, up or down, we can comfortably squeeze into additional levels of priorities. And similarly on the phone, we can trigger a selection and save by making these small up and down scroll movements, and after that swipe to the left and right to encode valence information. This is actually taking advantage of the fact that the content will, for the most of the time, move along with the touch point on a mobile phone, provided that there's only one touch point on the screen. So you might be wondering why wiggling? So naturally, we took a iterative design process to find an interaction that would be accurate enough to select the things that we want, and also be very efficient to perform, and is expressive enough to be able to encode our mental judgments, and last but not least, can be nicely integrated into all the gestures and interactions that we already perform and do not interfere with them, right? So after lots of initial prototypes, such as drawing different shapes to mean different encodings, we found that the current wiggling gesture strikes a nice balance between a lot of these properties. So for example, prior work has shown that when doing the active reading or learning tasks, people often unconsciously have their mouse cursor follow their gaze. So the cursor may already be available to wiggle on the content that they are interested in, as opposed to move it all the way across the screen. And also, compared to the conventional way of selecting text by clicking and carefully dragging the mouse cursor, wiggling doesn't need you to click your mouse buttons, which, believe it or not, itself is a cognitive decision, or you don't have to be super precise in terms of your mouse cursor movements, which requires some fine motor skills. And also, perhaps most importantly, we can naturally end the wiggle with a swipe to different directions to encode additional properties of the information that we are collecting. So, and our informal testing has shown that the time and effort to actually to perform that additional swipe is negligible. And the wiggling the cursor on desktop hasn't really been tapped by any of the existing applications, and the up and down scrolling movements hasn't been overloaded by any of the mobile operating systems. And last but not least, the back and forth or the up and down pattern is also pretty unique. It is practically robust against false positives, meaning that in general it is pretty hard to mistrigger a wiggle when moving your mouse around in your day-to-day use. So to make the wiggling technique more concrete and also more usable and testable, we've built a sense-making system that encapsulates the wiggling technique that allows you to save and triage clips of information into a holding tank, and supports filtering, sorting, and archiving, and you can later move them into the topics view for further organization. And we call this prototype WiggleLite. So here's the fun part, which stands for Wiggling for Information Gathering and Generating Lightweight Impressions for Triaging and Encoding. When I first started my PhD, I would never imagine that I can write a paper with the word wiggle in the title, but here we are. And no, it is not an acronym for a real rock or gemstone. This image was actually generated by DALL-E using the prompt, a piece of rock that is called WiggleLite, which shows lots of wiggles on the surface. I sincerely hope my advisor Brad is okay with this. So that was a high-level walkthrough of how WiggleLite works. For evaluation, we conducted a lab study to understand how well it can help people collect information as well as encode aspects of their mental context when doing sense-making tasks, compared to a baseline system which offers text and screenshot clipping features that people commonly have access to, and users can manually attach notes to the clip-ins to express their mental judgments. And note that the study was done using the desktop version, and we leave the proper evaluation of the mobile version for future work. So in the end, we found that using WiggleLite incurs significantly less overhead cost, which means that people were better able to actually focus on reading and comprehending the actual web content that they should be focusing on. And also, in addition, it also helped participants speed up their sense-making processes. So these evidence speaks to the efficiency design goal. So what about the other design goals? If we look at the expressiveness, participants collected almost twice as many clips using wiggling compared to the baseline, and almost 80% of them were either encoded with a valence or a priority, which suggests that people indeed were able to use WiggleLite to naturally express their judgments towards information that they just collected. And last but not least, if we look at the false negatives, 3.5% of the wiggles were misrecognized. It's either due to the wiggle did not activate or it collected something that the participant did not want. but there is no false positives, meaning that normal mouse movements and actions would not trigger a wiggle. And these are fairly robust numbers, I would say, and suggest that at least with the current prototype implementation and with some training beforehand, which the participant received before the study, wiggling is accurate and also do not interfere with existing interactions and user behaviors. And future work can improve the recognition algorithm to further lower the false negative rate and potentially investigate if and how people's wiggling performance changes over time. And participants also thought wiggling provided them with a fluid workflow when sense making. So for example, I just wiggled and move on. In fact, when I'm wiggling on something, my eyes are already on to the next paragraph. No more stopping to do the regular clipping thing anymore. And also, participants wondered if they could customize the system, such as by writing some sort of plugin to map the different directional swipes to what I want, depending on the situations I'm in, which, as I mentioned, could very well be a future direction that we can explore. So, to conclude, there's a high cost involved for people to efficiently collect information they find for later use, and at the same time externalize their mental judgment about that information. In this case, the valence and priority, while doing online sense-making and exploration tasks. And to address that, we explored the design space of some lightweight interactions and introduced a technique called wiggling that enables the collecting and triaging of information in a single gesture that works on both desktop and mobile devices. We also envision that this technique can, in the future, maybe be customized by users and extended to support a wide range of custom actions, possibly beyond sense making. That is all I have. Please feel free to ask any questions, and I hope you enjoy Andrew's talk later in this session. Thank you.
Any questions?
Konrad Limpert, HKI. I like the technique. I'm taking a ton of screenshots usually, so this would be nice to have. I'm wondering if you thought about how to make it discoverable, like how should people learn about this technique? Is there an intuitive way?
Mm-hmm. Yeah, that is actually a great question. We thought about this a lot. In the end, we kind of try to strike a balance between it being not super obnoxious, or because right now the wiggling, notice that you don't have to sort of click any mouse button. You just start to wiggle and it will automatically be recognized. We don't want it to be the way that the other sort of collection mode does it, which need to click some button and then enter that mode, and you need to remember to exit that. So yeah, the discoverability is actually something we need to work on. But yeah, I think that's a good question.
Thank you.
Yep. Thanks. You want to set up, or?
Please set up.
Yep.
Hi, I'm Cassidy Trier from the Allen Institute for AI, and my question was, how fine-tuned can you get with the selections? Does it really only select a whole paragraph, or can you select like one word or part of a sentence?
Mm-hmm. Yeah, we actually talked about that in the paper, but yeah, great question. Right now, I think if you do like a small size wiggle, it will actually lock onto a word. If you do like a bigger size wiggle, it will do a paragraph. And if you wiggle over multiple content blocks, it will just grab all of them together. And we actually have a nice graph that shows as the size grows, conventional selecting technique will take much more time, but the wiggling time is just flatlined. So, all right, thanks.
Let's thank Michael once again. So next we have Junyi Zhu from MIT, and Junyi will be talking about this project, Muscle Rehab, which is a great collaboration with Massachusetts General Hospital and Northeastern University.
Thank you, Anhong, for the introduction. Can everyone hear me? Okay, perfect. Hi everyone, welcome to my talk. My name is Junyi Zhu. I'm currently a PhD candidate from MIT CSAIL, HCIE group, working with Professor Steffi Müller. My research focuses on design and fabricate personal health sensing devices. So you might find my talk a little bit different from most of the paper in this session, but be diverse and open-minded as we are, I'm sure we all have a good time. So today's project is improving unsupervised rehabilitation by monitoring and visualizing muscle engagement. Before I jump into the details of the project, let me first introduce some of the background. Physical rehabilitations assist a person in recovering from muscular injuries. It can help people with get back, keep, or improve abilities needed for daily life. However, there are not enough physical therapists to assist the need of all people due to the population age and higher rate of severe health conditions, even within the same age group. This holds true for both developing and developed world, which leads to the WHO's call for action, scale up rehabilitation. Let's take a closer look at what physical therapists' essential tasks during a rehabilitation section. So there are mainly 3 tasks. At the beginning of the rehabilitation session, they will first determine patient's condition and then create and guide the training sessions for this patient. And last, they will correct the exercise mistakes and evaluate the performance and then move on to the next step. Several efforts has been made to remove the burden from the therapist by outsourcing one or more of these tasks, mainly the last 2 tasks, which leads to the unsupervised rehabilitation sessions or tele-rehabilitation sessions. In fact, the state-of-art unsupervised rehabilitation sessions are enhanced with sensor-based techniques, namely motion tracking. However, motion tracking is not really representative of what a physical therapist do, which usually determine on the muscle engagement instead of the motion. In fact, some of the postures during the training can be triggered through different muscle groups. In this project, we investigate if monitoring and visualizing muscle engagement during unsupervised physical rehabilitation improve the execution accuracy of the exercise, and if this additional muscle engagement data helps the physical therapist of their remote post-session evaluations. To do so, we built Muscle Rehab, which is an electrical impedance tomography and optical motion tracking enhanced rehabilitation system. It tracks users' motion via optical motion tracking and the muscle engagement using EIT, and visualizes on the virtual muscle skeleton avatar. Let me first walk you through the Muscle Rehab system. It has 3 main parts. First is the optical motion capture system and a custom wearable EIT sensing devices, as well as the rehabilitation user interface. To start with, the optical motion capturing system was built on 29 high-speed optical cameras, as well as 39 trackers that put onto a tracking suit. This is a clip of real-time capturing and mapping of our system. In case you're wondering, that was not me dancing. I hope I can dance like that. So the next is the custom-built wearable EIT sensing device with 3D volumetric measuring configurations. At the heart of the device is our custom EIT sensing board that we developed on top of my previous work, EIT Kit. Left is the main sensing board and can be flexibly extended with a stack of modular mux boards, which together they support up to 64 electrodes and 4 electrode arrays simultaneously of the EIT measurement. We put in total 32, so 16 times 2 electrodes set up and attached to the user's spine over 2 Nintendo Switch stripes to get the raw muscle engagement data. Let me provide a little more detail on how we visualize it onto the avatar. So basically, we get the raw data from the device, and then we constructed the 3D volumetric image. We extract out each of the muscle engagement data based on that, each of the 4 groups, and then we map that data. We extracted of them and interpolate them based on a scale of -1.0 to 1.0, and then we map onto the muscle skeleton avatar, which we build upon the biology 101. And each of the muscle group is independently modeled and rendered. Here's a clip of the raw and interpolated data for muscle group around the thigh. which is quad, hamstring, adductor, and stretchers. Last but not the least, the rehabilitation user interface, which is implemented in HTC Vivo Pro 2 VR headset. Notice that it is not necessary to be displayed in VR. We chose this because it's immersiveness, so that we can have more controls over the user study that I'm gonna show in a minute. From left to right, we have the training tasks, and then the ground gold standard, which is recording from the PT, physical therapist. The middle is a streaming avatar, which we put the muscle engagement visualizing on. And then on the right, it's the closer zooming look, as well as a audio feedback. Now that we have the working system, next is to deploy it with the real users. The first use study we do with the hypothesis that performing unsupervised physical rehabilitation with real-time muscle engagement visualization in addition to motion data will result in a higher muscle engagement accuracy during the rehabilitation exercise. For that, we recruited 10 participants, 4 females, 6 males, and the 2 conditions are designed and followed within subject design. We use randomized orders to avoid order effects in all the participants. The 2 conditions were visualizing towards the users with motion data only versus visualizing with motion data plus the muscle engagement data. Upon the suggestion from our collaborators from Harvard Medical School and Mass General Hospital, we choose TKA rehabilitation protocol. We measured the muscle engagement accuracy by first calculating the time where the engagement muscle matches the correct muscle groups that was suggested by the physical therapist. And then we divided that by the overall time of the session, and then use that as the percentage of the accuracy for the comparison. Let me give you a closer look at of all the cool exercises we're doing, and also a clip from the user study. I'm showing this mainly because it's a super cool clip. In fact, 3 out of our 10 participants changed their social media profile image after the study. So some people, at least some of them enjoyed it. Here's the quantitative results of the study. Some of the key takeaways are, on average, the condition with the muscle engagement data visualization achieved around 15% more accuracy compared to the motion only. If we zoom in a little bit and look at these few exercises, it turns out that the exercises with higher difficulty levels and non-conventional postures, like single leg deadlift, standing fire hydrant, tends to have even better result. We also noticed some outliers, like sit to stand, which actually people achieve higher accuracy without the muscle engagement data. The hypothesis is that maybe the exercise is very common in the daily life, so by showing the additional information might be actually distracting them from performing naturally. To evaluate if the muscle engagement is helpful for physical therapist for the post-rehabilitation evaluation, we conduct the second user study, which again, the hypothesis is that displaying the muscle engagement data in additional to the motion towards the physical therapist will help them perform a post-rehabilitation analysis that's closer to the on-site analysis. For this one, we recruited 6 licensed physical therapists, 2 females, 4 males. And then we showed them the recorded video from the user study 1, both on-site videos, as well as the screen recording of the VR headset, so that we can mimic a video-based remote therapy session. And then we compared that with one on-site therapist who was being with us during the user study 1 and doing the real-time evaluation. We compare whether which condition have like the closer results towards on-site analysis. Again, here are the quantitative results. And again, the key takeaways is indeed, with the assistance of the additional muscle engagement data, the remote evaluation tends to have closer results towards the on-site analysis. Some of the therapists reported that having the muscle engagement data available would actually facilitate the communication with the patient, because they can, look at the video and then point to them which exercise and doing which posture they're actually engaging the wrong muscles, which can be quite helpful for their, for the re-evaluation and then the next teaching training of the next session. They also suggested that to integrate more of exercise motivators, as well as putting more additional viewpoints. In the next session, let me break down some of the implementation details of our system, mainly on the muscle engagement sensing. So, as I said before, we used electrical impedance tomography. Electrical impedance tomography, or EIT, is a non-invasive image technique that measures the conductivity, permittivity, and impedance of a subject. As you can see on the left, it works by attaching electrodes around the surface of subject, and then use the electrodes to either injecting or measuring the resulting voltage. Based on the voltage measurement data, it can reconstruct an image of the subject's internal conductivity. Little bit details on on how we actually solve this. Basically, we solve the problem of interfering the internal conductivity over domain omega, over the voltage response and the current source, with the origin frame that usually initialized to be a constant conductivities. This is mathematically formulated by Ohm's law and Ampere's law. And under the assumption that there's no internal current, we can reach to the bottom function. Then we solve the forward problem and then the inverse problem with the experimentally chose current sources I, which is the current we're injecting, as well as the measured boundary voltage phi, which is the measuring result we have. Based on these two data, we can basically minimize the function of the bottom one, the boundary function, towards the domain function, and then we can basically approximate the internal conductivity distribution based on that. Since I'm running a little bit out of time, I will be coming a little bit faster. In order to achieve our goals of muscle engagement measurement, we did a few custom modifications over the conventional construction algorithm, as I just mentioned before. First is we use the 3D instead of the 2D reconstructions, and then instead of the conventional adjacent patterns, we use actually this zigzag or SIGCHI, injecting a measurement patterns, so that we can get more data among the cross-section between the two arrays. We also build this custom forward models, which with the predefined sigma 0 or origin frames, which will help the algorithm to find the starting point and have a ending result that's closer to an actual cross-section of a human sign. In the last section, let me quickly discuss some of the limitations and future work. First is the display modalities. Although we displayed everything in VR, but as I said before, that was mainly because of the requirement for the user study immersiveness and study parameter controls. But the same data can be displayed on various of displays, such as ARs and 2D displays. For our study, we use the best motion tracking system we can find, the OptiTrack, which is normally used in the movie settings, so that we can eliminate the possibility of the inaccuracy of the motion data that's by injecting the noises into our study result. During the normal real-life practices, users can use the conventional available trackers from the VR headset, which we believe that with less accurate motion tracking system, the effect of the muscle evaluation that can improve will be boosted. Next is the multiple EIT devices, which currently we only have one device on human. We're thinking about having multiple of them so that we can have a more historic image over a larger part of the body. Last but not least, we would like to provide additional feedbacks. Currently, the system provides the visual and the audio feedbacks. For the future work, we're exploring to provide haptic feedbacks as well to simulate the touch by the physical therapist doing a session, which can point them exactly which muscle they're doing wrong and which muscles to be engaged. This can be achieved without additional hardware adding, because we have the active current sources and the electrodes all over the place, so we can potentially implemented what we call the EMS, or electrical muscle stimulation, and then use that to achieve the simulated haptic feedback. With that, thank you everyone, and I'm ready for questions.
We'll have time for one short question. Yeah. And Andrew, please set up.
Hi, Claire from the University of Washington. Can this system provide like the degree of activation? Because I know that like other like EMG can, for instance.
You mean if they both working together, would it?
No, like how hard are you activating your quadriceps?
I think compared to EMG, the IT in general compared to EMG, if we're talking about like the non-invasive one, like the SEMG, it works really great when it's at the right location on top of the muscles, because it is the voltage, that responses that triggered by the neural system as we're measuring. However, if you're thinking about muscles, they tend to have layers underneath, so those signals are not be able to obtain unless you're invasively using the EMG. The other thing is that for the EIT, because we're measuring the cross-section expansion and contraction plus the blood flow through the muscle, so we can measure both the contract and also the stretched muscle, whereas the EMG, which generally only measures the contracting part. So I think that was the thing. Yep, thank you.
Let's thank Junyi once again. Okay, so next we'll have Andrew from Carnegie Mellon HCII to present work on this comprehensive system on in situ sense-making support in the browser. And I also want to announce that Andrew is looking for an internship this summer, and Michael is on the job market for industry positions.
All right. Can you hear me? All right, yeah, great. I'll just be using a second laptop here so that we can still get presenter notes and whatnot. All right, cool. Yeah, so hi, my name is Andrew. I'll be presenting Fuse, in situ sense-making support in the browser. And so if you've ever, here, let's try to get this video working. If you've ever tried to collect information online and put it together, you quickly realize it's a very overwhelming process. You're going to be probably going back and forth. As you're kind of extending and going beyond what your brain can really hold, you're probably going to have some sort of reference document, which is usually a Google Doc where you're putting things, you're trying to throw things in there by clipping them. You might be annotating some of them. And then finally, you're probably going to be trying to herd that into a format that'll work well with actually reading it, actually being able to look back at it in maybe the 24 hours or however long, maybe 2 months that you're going to be looking for headphones. So this is a very difficult activity to do as soon as you start clipping a lot of content. In particular, what we're going to want to do here is we're going to want to collect all the types of information that we're collecting online. So we're going to want to be able to collect videos. We're going to want to be able to collect the context of those videos. And we're also going to want to be able to collect why we wanted to look at this specific snippet of web content. We're also going to want to decrease that cost of going back and forth. So ideally, if we could, we would want to organize in the same space, going back and forth, and as our model of how they should be organized evolves, we should also be able to quickly go ahead and do that in the same screen. Lastly, to keep things fairly compact as we pull these clips in, we're going to want to bundle these items or at least visually compress them so that as we're collecting a ton of clips, a ton of notes, we can still see our entire collection or at least access it in a way that we can keep it fairly compact but then expand whenever needed. So previous systems have largely looked at this problem through text. So some of the systems, what they'll do is they'll have an in situ system that'll focus on text, and that is very nice because you can go back and forth and you can actually have access to that. But unfortunately, it doesn't have as much visual structure, and it doesn't support all of this rich web content that we might want to have. On the other hand, some systems do enable that, but they require some sort of algorithms or some kind of template that we defined ahead of time where we extract that content and then show it in a summary table. Or alternatively, we have some sort of different view where we're able to pull that in and then look at that. So ideally what we'd like to do is we'd like to fuse these two. We'd like to have a system that allows us to have a sidebar in situ, and we'd also like to collect all sorts of web content, and if we want to collect a video, we want to collect a text, we want to collect a snippet, we should all be able to do that fairly flexibly. So what would that look like? In our case, it looks like an in situ sidebar that would sit alongside your main browsing context. And that sidebar would have to balance some big ideas that are naturally kind of in conflict with one another. So for example, you'd want to rapidly collect things, you'd want to view and organize everything in situ, and you'd also want things to be fairly visually compressed, even though you're usually collecting a lot of stuff. So what would that look like? We have a little video here. Let's see if that'll just play. All right. I don't know if... That was Fuse in action right there, a nice little video there. So what we did is we built this system and then we publicly deployed it. I tried to understand the value that users would get out of these features after we iteratively developed the system. We had a public deployment of about 22 months. It was public, free to use. Anybody could use it. We had about 134 participants that decided to use it for their activities, about 400 projects on a pretty large variety of domains. So in terms of the types of features that Fuse had for allowing to collect these variety of content, we implemented text highlighting, we implemented image drag and drop, and classic bookmarking, as well as bounding box clipping and tab importing. In the background, Fuse also collects provenance information such as what page things came from. In some cases, it also takes a viewport screenshot if the type of content you're grabbing is not an image itself. This becomes relevant a little later. Users found these features to be very useful for a number of reasons. In particular, Lightweight Capture allowed them to quickly grab everything that they were looking at as they did some sort of other activity. So for example, shopping, they were able to grab all sorts of stuff, and people said that, okay, well, if I'm shopping, I can just easily throw it in, come back to it later. It wasn't a big barrier for them to do that externalization. In addition, they found it really useful because then they could immediately go in and focus on annotating the content as opposed to actually grabbing it. And so you see people in our interviews, follow-up interviews, talk a lot about how, well, I can go ahead and look right at what was important, take a quick note on that, and then move on. Fuse also had a number of features that we implemented and kind of thought about and iteratively developed for in-situ organization. In-situ organization is difficult because you're trying to do all this organization stuff, but you're doing it in a very compact space off to the side. And so to make that pretty easy, what we did was we focused on having a standardized card-based UI. And so we had these card-based UIs that we used some of that provenance information that we're automatically collecting to populate. So we would have this viewport that people could look at and remember the context. We would show where the site came from. We would show the different notes. We would also allow people to make hierarchical structures using a traditional folder-based method. And we also allowed them to prioritize and reorder things in these more classic ways that people organize their information with color tagging, just reordering the stuff literally, and pinning them as well. In addition, we ended up creating an interaction that we called container cards, which I'll talk about a little later, that made these hierarchical structures much easier to manage in that very compressed space. People found a lot of these features very useful, and I'll just highlight a couple of reasons that they found them useful. So for starters, being able to have access to that organization right away made it very easy for people to think about, oh, well, I could just go in, quickly organize it. I don't have to pop out that overhead that you traditionally see with those applications. It didn't exist for these users. And so they felt more encouraged to use it. Another thing that was particularly useful about having it off to the side is they could see their entire collection all at once. So because of that visual compression that we'll talk about a little later, they were able to quickly look at what they were searching, look at what they had, and then quickly skim, oh, I already had something here, and then go on and browse things. And it became very easy for them to pick up where they left off. Lastly, a bit of Fuse's secret sauce, one might say, is the container card and these bundles. So one of the things we realized as we started building hierarchical structures with folders is that they would end up being rather deep. And as a result, they wouldn't quite fit in the bar. So we started realizing, like, what do people want out of that hierarchy? And we realized that people want to cluster evidence together, for example. So if you were looking at a restaurant and you had many different pictures of food that you were excited about, you could just bundle that under a card without making a folder. You just pull it right in there. So there's a couple of interactions that assist users in doing that in Fuse. We have the container cards themselves, where you can just drop and import cards into a card, and that makes it into a folder itself. We have a peek interaction that allows people to hover over a specific container card, and that allows them to see what's inside. And then we also have this reader view that allows people to expand that and look at their notes and just make a deep dive. People found that particularly useful, and I'm going to highlight that in a number of ways. People ended up trying out, and a lot of people, 42%, I believe in the paper, of people created structures and like hierarchical structures, and a lot of people ended up using container cards instead of traditional folders for that. And some of the things that container cards really helped people with was to help jog their memory, because they could use the peek interaction. They could quickly understand, oh, this is all about this specific type of aspect of maybe this product or maybe this thing I was considering. It also really helped them think about things in spatial terms. So if they were looking at a large amount of items, there was one user participant that was talking about organizing hundreds and hundreds of poems. And so he found this particularly useful as he could think about those in a spatial way, sorting things, prioritizing them because of that visual compression. In addition, we also had a chance to qualitatively code these projects to understand what people were using Fuse for. We didn't pay anybody to use Fuse. It was just free to use. And we wanted to see what types of things people found particularly useful in terms of what types of tasks. So we found these 4 main categories of user intentions and one extra special one that I'll talk about here, which isn't a category itself, it's just something we witnessed and I want to talk about here. So for the first one, we found a lot of people would try to collect things about a specific subject to learn a lot more about it and attempt to aggregate that into almost like a wiki-style page for themselves, but without a huge lot of notes. It was really about collecting, clipping, and occasionally synthesizing. And we found that synthesis itself was rather rare in our tool, so people were not usually combining items. And we think that's because simply having the clips within Fuse may have been enough synthesis for them. Some examples that we saw, people researching cryptocurrency, people understanding monetary policy, people trying to learn a coding language. Another very common thing that we saw was people attempting to compare items. So for example, maybe trying to decide a lawn service to purchase, maybe choosing a vacation destination. And there are a lot of many different activities that we saw that composed this activity. For example, people extracted features, but there was also this long tail of activities. People would note judgments on a specific criteria, like this is too expensive, or they would add supporting evidence, like pictures for a restaurant. And occasionally they would also point out a dependency, like if I need to buy these AirPods, I need to buy this case, or if I'm buying this piece of furniture, I want to buy this other piece of furniture. Another one that we thought was a more advanced form about learning about a subject was building a self-reference. And so this category was characterized by very lengthy summaries of documents, as well as extensive extraction of key content. So people would often paraphrase blog posts at length or write a reflection after reading a research paper. For extracting key content, people would very often copy and paste abstracts, or they would copy and paste a very specific type out of the data so they can have it to reflect on and look at. Sometimes they would also paraphrase different tips regarding a career or designing a website. And so we think this might be a more evolved form of learning about a subject where you're starting to put a lot more notes into this. Lastly, we had this thing that was very, very common, even though it's not very complex, and that's just having access to quickly having access to things that you use every day. And so that's very likely driven by the fact that Fuse sat in a sidebar alongside everything you were browsing. You could collapse it, but it was always there for you. And so a lot of students would use it for coordination materials, a Google Drive, or something that they had to access frequently, maybe materials for a class that they were taking. There was also a couple of interesting things that we saw with almost like a mood board. So people would have this thing on the side, and they would have links that they found pleasant to look at, or just wanted to occasionally look at because they were bored, or they needed it for some other reason. Some examples are artistic inspiration, pictures of past vacation destinations, or religious texts. There was a user who put a Bible on the side. The last category I'm going to talk about wasn't a category in and of itself. It was rather a fairly interesting user behavior. So even though Fuse was not built for task management, we saw that about 15% of projects had some sort of self-management of projects. So I've just broken them down here. In those projects, what we saw is typically people would have to-dos. They would sometimes label things to read later or to process later. Sometimes they would record the state of an item. So I've only read halfway through this. And then lastly, a small amount also just posed open questions in free-form text. So I'd just like to go over some takeaways as we built this system that allowed people to go back and forth and collect and organize in the same pane. We found that users did find in-situ organization very useful for a variety of domains and tasks. And the way that they found them useful differed whether they were comparing items or they're trying to collect information about a specific monetary policy that was enacted. We also found that visual compression was a key driver for people to find Fuse useful, because that visual compression allows them to see their entire collection, which allows them to think about their collection differently. It also allows them to quickly jump back into their collection because it's very visual. There's images, if you didn't write enough notes, you could at least recover a lot of that context from the screenshots or some of this other automatic information that was collected. Lastly, I'd like to point out that these kind of 4+1 common user intentions that we saw are likely relevant for other systems builders that are making sense-making systems, and might be a start that when you're building kind of a general purpose sense-making tool, you may want to consider that these are things that people are going to implement in their daily lives using your system, whether you expect it or not, especially task management. You'll probably see some people implementing that in some form. So that is all. That's Fuse. And I'd like to obviously thank my collaborators, without whom such a large technical system and deployment would have not been possible, many of whom are in this room, like Joseph. But thank you, and I'm happy to take some questions.
Hey, Andrew. Great work. I'm Rock. I'm from University of Washington. I have a question about, so you talked about this as a public deployment project. So do you know who are the, I guess, the users in your sample, like their employment or their demographics and something like that?
So we did not collect some explicit information about our users because we had them use it, but we did reach out to a set of users that we collected those demographics for. So we reached out to a set of users that had been using our tool quite a bit, so they were very experienced in it. And so in those interviews, we have a set of demographics and things like that that further contextualize their interview. Yeah.
Oh, so like for the user who would use it, who you would use Fuse for project management, like who are those people typically?
We don't have concrete demographics on that type of information because we tried not making it feel as intrusive when they were using those tools. We wanted them to use these tools for their own use and not have to worry about, hey, I put in all this information. I don't want to feel like I'm being tracked through the stuff I use for my daily life. Yeah. So we don't quite have data on that yet.
All right, thanks. I have one more question. Sorry about it.
Go for it.
Well, I guess I can. Sorry, I can talk. Shut up. Oh, sorry. You just said that collecting information is common, but synthesizing information is rare. So I'm wondering if you think about, you're currently thinking about like automatically characterizing the information that user collect would be potentially future work you would pursue.
Sorry, if I understood correctly, you're saying that like synthesis would be more of future work. Am I understanding correctly? Automatically synthesizing. It's possible that in our system, simply having those clips and notes together in a way that you kind of have visual compression and you're looking at this all in one place was enough synthesis for these tasks. Because a lot of these tasks were driven by, I want to purchase a set of Christmas gifts. And it's possible that they did not need very complex representations to make that decision and to kind of move on to other daily tasks.
Hi, I'm Yellow Lego Brick from Stanford University. I want to sort of give you a soapbox a little bit to opine on something. You're walking this very challenging line here where you're providing incredibly powerful and useful tools for collecting information, doing sense making, and so on. And yet you're also having to struggle against the sort of defaults that you critiqued at the beginning of the talk, the sort of Google Docs, the Evernotes, the sketchbooks, the to-do.text kinds of situations. And I want to hear just for a moment, having done all this work, at this point, what do you think are the kinds of hooks that really drag people out of those general purpose tools and into something specialized like that you've created? And what are the kinds of approaches that we would think of but are kind of like honeypots, don't quite pull people out of those tools? What do we have to do to sort of be providing enough value to drag people out?
Right. So I think in our case, what we saw a lot of people suggesting we do is provide hooks into their workflow. So for example, we have this general purpose tool that allows people to do sense making on literature review. A thing that people commonly wanted is then to cite, for example, which is part of the workflow that they use. So I think if we consider some of those common user behaviors, like taking notes and whatnot, within the context of the workflow they are in, I think that provides a useful bridge between a semi-structured collection of clips to then, okay, I'm citing and maybe I'm throwing this into a LaTeX file, or I am using that more concrete, maybe domain-specific bridge. But that domain-specific bridge, I think we can predict using some of those, some of the feedback we got and some of the activities that we saw in terms of task management or taking notes on things or aggregation.
Awesome. Let's thank Andrew once again.
Thank you. Thank you.
Last but not least, we have Yihao Peng from Carnegie Mellon presenting this system to support collaborative mixed ability presentation authoring, like with co-authors from CMU as well as UT Austin.
Cool. Whoa. Okay, can everyone hear me? Great. Happy Halloween. I think it's the last talk of the holiday, so I'll just wrap it up soon and let's go to the party. Yeah, but hi, I'm Yihao Peng. I'm from CMU SIGCHI, and today I'm happy to share our work. It's called DeepStriker, a system that describes visual design change to support mixability, collaborative presentation authoring. So this work was done with my lab mates, Jason Wu, and my advisors, Jeff Bacon at CMU and Amy Pavol at UT Austin. So everyone creates slides for both professional and educational setting. However, existing slide authoring tools are not accessible to people with visual impairments. And this is because the slide authoring tools convey the layout and style information only visually. Therefore, it is difficult to interpret with screen reader. And I'm gonna show you an example. So imagine you are reviewing a slide without seeing it. You use your screen reader to read the text on the slide that says it's an audiobook.
It's an audiobook, text box layout item.
If you want to know how the text is laid out on the slide, here's the information you will get.
Actions available. Size, 171.7 points wide, 26.3 points tall. Position, 19.1% from left, 83.3% from top. Right 2 points. Position at 185 45.43 points X and 449.89 points Y scale.
So that's actually hard to understand. From a screen reader, it's challenging to understand the overall layout of the slides. So for example, this slide, the title is on the top left of the screen, and below that, 3 image text pairs are displayed horizontally with image at the top and text at the bottom. So to better understand how blind people usually author slides despite the limitation of existing tools, we conducted a formative interview with 9 blind presentation authors. All authors in our study report that they write the content of the text, content of the slides in a plain text or a slide template with bullet points. Then they send it to their collaborators, who revise the design of the slides and then send them back to the authors. While blind authors value the expertise and efficiency of their collaborators, the collaborators often didn't fully describe their slides and changes, making it difficult for a blind author to understand and provide feedback on the revisions. So the goal of this work is to help blind presentation author understand the slide's visual content and change so that they can be more fully engaged and participate in the slide authoring process. We present Describer. Describer takes an original slide and revised slides as an input and automatically analyzes the change made to the slide content, layout, and style. Then provides the change to the presentation author as a Google Slide extensions. Our interface includes a slide content list and a change description list. Let's talk about slide content list first. So using Describer's extension, authors can first review the content on their slides just like what they can do with existing tools, where the elements like title, image, and text are displayed. So here I will use the screen reader to read the slide background image and title.
Background image, a white wallpaper with confetti on it, menu pop-up, title. What's amazing is it's menu pop-up button.
When reading through the slides, author can access style of individual slide elements, including font size, style, and the position of the slide title.
Menu, 5 items. Menu, 5 items. Size equals 53px, color equals bold pansy purple, font equals Oswald button.
Describer also helps author identify slide change with the change description list. To use the change description list, author loads the original version of the slides and revised version of the slides from their collaborators, and generate a list of change that accord between 2 slide versions, including revision to the content, layout, and style. The content changes describe change to the slide content. For example, here the collaborator add a background image with confetti, an illustrative photo for each bullet point. Revise the text of the slide title and bullet points. In this example, the author used the screen reader to review the change to their original slide content.
Slide 2 content changes. Added background image of a white wallpaper with confetti on it. Added image to the top of each bullet item in the horizontal list.
To learn more about the content change by authors, the users can navigate to the elements for lower level details. So for example, the author can navigate to change about adding illustrated images about the slide text to hear low level details about the change.
Menu, 3 items. Menu, 3. Added an image of a man reading the book while listening to its audio to the top of first list item. Added an image of a woman holding a CD, which is an old technology, to the top of second list item. Added an image of a QR code being scanned on an iPhone to the top of third list item.
After reading any change, authors can activate the edit mode with screen reader to directly edit the slide content by clicking the update button. Here, the author has noticed that the slide title has been revised by reading the content change. So they added the new title from What's Amazing Is It's to What's Amazing Is.
Slide 2 content, edit, button, group. Update, edit text, background, edit text, title, in edit text, title, title. What's amazing is your space, I-T-S, comma. Out of edit text, update, button.
Let's talk about the layout change. The layout change describes how the overall layout has changed between the 2 slide versions. Describers share changes about the layout as a whole, as well as group of slide elements. Describers' overall layout change share how elements are positioned relative to the title. So here Describer shares that the title is placed on the top left of the slide, and 3 text elements with 3 images elements are placed below the title. Describer also should change to the group of elements. So here, describer shows that the list has changed from vertical to horizontal. Finally, describer should change to the slide style. The style changes describe how the style of the slide text changed during revision. For example, here, describer shows that the title has been changed to a larger and use a bold pussy purple color. Describer also shows that the color of bullet point text has changed to bold amaranth. Describer's interface is powered by several algorithm methods. First, describer extracts and describes slide elements in both original and revised slides by fusing the information from both web crawler and Google Cloud API to retrieve the metadata and the description of the text and image elements. Next, describer computes the alignment between the original and revised slides, and finally corresponding element between edits. To determine element correspondences, our system first encodes each element using CLIP, a present visual language model that projects visual and textual data into the joint vector space. Describers then compute the pairwise cosine similarity between each original and revised slide element embedding. Since each element can result in a number of mapping between edits, we take the correspondence mapping process as a machine translation task, where each of the token in the original sequence can have 0 to multiple mapping to the token in the revised sequence. So this process is similar to finding the word alignment when translating from English sentences into other languages. We apply an unsupervised sequence alignment algorithm to iteratively match the elements to find the optimal alignment results. The final step is to generate descriptions of the change between slides. Once we compute the corresponding element, we determine what types of change happen. So for instance, the original title, "This Catch Your Eyes," corresponding to the new title, "Got Your Eye With." Describer detects the content and style of the title will change by comparing the text and style properties. Then applies a template for each changed type to gather final change descriptions. For example, one final description shows that the title has been revised to "Got Your Eye With." Text can also correspond to images. For example, the text that says to add a photo of a book cover corresponds to the image of that book cover. The final description thus shows that an image of the book cover has been added to replace that text. Elements without corresponding elements in the original slides are new. The change description showed that a new element has been added. For instance, one change description says, "Add background image of a white wallpaper with confetti on it." By detecting the position of corresponding elements, we describe the layout changes with respect to the title, such as place image to the bottom of the right or of the title. To understand the efficacy of describers' visual change descriptions, we conducted a user study with 6 blind presentation authors to explore if the change description helped blind authors more engage during mixed ability collaboration authoring. Specifically, we asked participants to provide 2 of their own drafted slides, and we then sent both of them to the professional designers on Upwork to redesign their slides, as if the participant and designer are participating in a collaborative presentation authoring process. We told the designers to freely change the text contents as well as the visuals to make the slides more professionally looking. We compared 2 interface conditions: accessible slides where authors have access to the slides before and after the slides, after the revision where they can read and compare them individually, and describer interface where the change descriptions were provided to the selected 2 slides. Each participant will view each interface with a different set of slide pair. During the study, we asked participants to report their number of identified changes and the revision they want to make while navigating through each interface. Our results show that participants identified around 3 times more changes using describers' change descriptions than the accessible slides alone. Describer also encouraged participants to provide 3 times more suggested revision and feedback. Participants report that Describer empowers them to have a visual understanding of slide changes and their impact on the presentations. Participants also report that Describer would inform their future slide authoring. P2 said that by understanding the change, they feel they will be able to start putting more personal style into the slides by learning from their collaborators' revision. Currently, Describer detects and describes content, layout, and text style changes. In the future, we will detect visual changes made to images and other visual elements as well, such as resizing, cropping, or even editing. We also plan to detect and describe changes across multiple slides rather than only one-to-one slide changes. For example, collaborators might split one slide into several slides. Finally, while slides are important for work and education, we plan to extend Describer to additional types of visual designs like posters, flyers, and even work documents. With that, I would like to conclude my talk. Thank you for listening, and I'm happy to take questions.
Great talk and great work, by the way. I'm Arjun Srinivasan from Tableau Research.
Thank you.
So could you talk a little more about how do you prioritize the number of summaries that you provide? Because, I mean, the examples you showed are great when the number of changes are 4 or 5, but what if I make like a lot of changes? And also, what if there's some animation or kind of non-static changes involved?
Yeah, So that's a great question. So basically, we try to prioritize or like basically order the changes based on the sort of the magnitude of the changes. So that's why usually when the element is newly added, we'll basically prioritize that at the front, and maybe it's like a revise the text content that's just a minor change, then we'll basically deprioritize that. And so that's like one of the strategy we'll kind of prioritize the part of the thing. In terms of like the summarization part, we basically try to aggregate the similar change types into like the summarizing sentences. Like for example, I show example that adding like a couple of images on top of each bullet point item. So in the first level of the descriptions, we will talk about adding images on top of the bullet points. And in the second layer or deeper layer of the description, we'll talk about what exactly elements was adding to what exactly bullet point item. And in terms of the animation, yeah, I think currently we didn't consider that. And the reason is because usually the collaborators not tend to adding the animation to the blind people's presentation. And it's because it's very difficult for like screen reader to actually understand what happened in the animation. So it's even harder to them to either consume or present it. So that's not in our consideration now, but I think it's a very good direction that we will explore in the future. Thank you.
Hey, thank you for the great talk. I'm Mina from UT Austin. So I was wondering, like, so after knowing the changes, I was wondering, like, if blind authors' suggestion for changes were mostly about like content changes or across like style changes or layout changes, because I'm assuming like maybe some of the style changes or layout changes won't make much sense to them.
Yeah, so that's also a great point. So yeah, so based on our study, like most of the changes that blind presenter suggests was content changes, and that's because they have more familiarity with that. And in terms of the style layout, I didn't show it here, but we do provide like sort of like some basic design guidelines in our style description or layout description. That basically, for example, if the font size is too small for this specific slides, we'll provide some suggestion so that they could sort of make sense of that to provide some recommendation based on that. But in generally, they are mostly still learning the layout and the style thing for the presentation or even just a visual document, because it's basically very new concept for them. So like I mentioned in the later part of the talk, basically they are not just using this tool as a authoring assistant tools, but more also like for the learning process that how do the collaborators try to change this slide style, like consistent, making it consistent with the title font, or making it consistent color across different slides. So I think it's a very challenging topic, and I guess we will try to look furthermore when we try to dig into the more independent slide authoring process with them. Yeah, thank you.
Thank you.
I think that concludes our session. Let's thank all the speakers once again. And please enjoy the rest of the conference.